Once you get past like the first couple of
Okay, it is officially 9 o'clock. Let's go ahead and get started with our final day. Y'all made it to day 5. Today's going to be a half day. We're going to start with Sean talking about PyHC chat, which you'll find out more about in a second. Barbara Thompson is remote, and she's going to be leading a bunch of intro to AI and ML and Heliophysics materials. So get excited for that. She's an excellent presenter. And then we'll just do a little bit of wrap up and then grab some food and go walk up a mountain. So thanks.
Yeah, sounds awesome.
Oh, and before we all completely leave for the day, let's gather outside of the front maybe and take a group picture.
I like that idea. Yeah. All right, cool. I guess that's my cue to take it away. I'll start by saying first, apologies for the voice here. I like randomly lost my voice yesterday, and now I got that combined with the morning going against me, but it doesn't sound too bad at the moment, so hopefully it doesn't get worse in the next 15 minutes. But yeah, like Julie said, the focus of today is kind of on like machine learning AI stuff, and really mostly it'll be more on like the old statistical kind of machine learning stuff, but we would be remiss if we didn't at least cover generative AI, because that is obviously the huge thing in this space right now. And I'm giving you a little talk to introduce you to PyHC chat, which is a chatbot that I built last year, basically just connecting OpenAI's GPT-4 to the GitHub repos of our core packages. And it's actually kind of amazing how far you can get when you just do that much. First of all, I kind of want to just gauge so that I know my audience here, like who's decently familiar with like the under the hood LLM stuff, like who's played around with AI, and do you guys know like what token limits are and that kind of stuff, or should I go a little bit more? I'm seeing like some head nods and some nah, so all right, that works. So I've got up here a RAG-powered chatbot for PyHC. RAG stands for Retrieval Augmented Generation, and that's basically just the main way that you connect external information to a large language model is through a vector database, and you let it retrieve information from it as it goes, and it's just become so popular now there's an acronym for it. But yeah, this exists right now. It is on GitHub. PyHC chat. I want to, in this talk, basically first give you some background to show you like what it takes to understand code bases with AI. And then I'll walk you through what PyHC chat actually does. And then I have a bit of a demo. It's a pre-recorded demo though, because I don't really have enough time for a live demo over here. But all righty. So when you're working with AI, a large language model can't learn a new code base unless it fits within the token limits, which is basically just the maximum number of things you can say in one conversation or prompt before it just gets overloaded and says, hey, you've said too much to me. And that was the major limiting factor for doing this kind of thing, because I can't just copy all of the GitHub repos of all the PyHC packages and throw it in one giant prompt, because that is just way too huge. So I got to do a whole bunch of rigmarole to get that to happen. And large language models can only learn things in one of two ways. You either have via the model weights or the model inputs, where model weights are basically the initial training data, like where you take that huge corpus of data and shove it through the large language model and do all that kind of stuff. Or even some of like the open source models now, and even cheaper versions of OpenAI's models can be fine-tuned. That would be doing stuff in the model weights. You can kind of think of that like the difference between short and long-term memory in a human brain, where long-term memory is obviously longer, but it's more prone to errors upon retrieval. And via the model inputs is more like its short-term memory. So that's things that you're basically saying to it in prompts during a conversation. And you really only have three main ways of doing this. You can either copy paste code snippets manually into a prompt and say, hey, ChatGPT, help me with this. But who wants to do that? You have vector store retrieval, which is what PyHC chat does, to basically automate the process of pulling out the relevant information for you. Or if the model has a code interpreter, it can actually basically crack open the repos and sort of read through it file by file, think, oh, I'm going to check in this folder. Oh, this file name sounds right. And I'll look through here. And that's pretty neat too. And Open Interpreter is a project on GitHub that is actually a part of my demo here, and I'll kind of see how that works. But I want to focus on vector store retrieval because obviously that's what PyHC chat is doing. So over here, do I have a cursor? Yeah, I've got a cursor over here. So this diagram is from LangChain, which is the framework that I built this on. And it's basically showing you the steps for this. So over here, you have your big AI bot over here and this massive data set that trained it. But when the user asks queries to it, instead of just sending the user's query straight to the model, you have this retrieval step first, where it looks at the query and it dips into your knowledge base, which is in our case a vector store, and it pulls out relevant context to include with the query so that the model kind of sees more information that it needs to know to answer the question. And this step here can be as complex as you could imagine. We use something called semantic search, which to do hand waving basically just takes a look at all of the text chunks in your database and returns the ones that are the most semantically related to the user's query. But you could do a whole bunch of crazy stuff like incorporating knowledge graphs. You could implement your own like custom search functions to help it find the right stuff. The rabbit hole can go very deep there. But this is the diagram of what my system looks like here. And it's pretty big, so I'll focus in on two halves of it. But I just want to say at a high level, kind of the way I thought about doing this was that we sort of have a committee of experts on the PyHC packages that it can talk to. So you have like one helper bot per PyHC repo, and then PyHC chat, as you're interacting with it, can go consult that little committee and get the helper bots information from it. And zooming in on how we create those helper bots, this is called the ingestion phase. And this is actually in general how you set up any retrieval augmented generation AI chatbot. The first step is I just took all the GitHub repos and I converted everything to text, like just plain text, .txt files. And then you take those and you split them up into chunks. And then you get what are called embeddings for those text chunks, which are like numerical representations of the text, because large language models are neural networks and they work with numbers. And then you just shove those embeddings in a vector store, and then the helper bot can retrieve from it. And then over here, this is the actual system in place. So there's a few bots that we need to know about to just understand this. First is, I already talked about the helper bots. Where did my cursor go? I lost, here it is. All right, PyHC chat is the main thing that you're interacting with. It's what's storing the chat history and giving you all the answers. But then there's a repo selector bot, which is its whole job is to basically decide which PyHC package is relevant to the user's query. And then repo prompter bot over here for the case where if more than one package is involved, it can actually formulate nice questions to ask the helper bots themselves. So this is the way we're kind of consulting the committee of experts, if you'll stick with that analogy. And you get the helper bots will pull from the vector store and they'll condense that and give it back as an answer. So one cool thing about how I implemented this, which is just a great thing about working with AI in general, is I do not have any Python code really inside the bots themselves. I'm giving them English statements, basically like written instructions like you would give a person to say, here's your job. And so these bots actually understand they're part of a PyHC chat system. And when they know that, it works surprisingly well. So over here, I've got a demo. Like I said, no time for a live demo, but There is a YouTube demo that I've just trimmed down to about 2 or 3 minutes, and I'm going to play through some of this just so you can see it in action, and this will show off the various parts of the system.
Rerun it in verbose mode so we can like see some of the inner workings of the helper bots.
There it's loading the vector store.
So like watch. If I ask an open-ended question like, how do I calculate alphane speed? The first thing that happens is repo selector bot recognizes that's a plasma physics question, so PlasmaPy is the relevant repo here. And remember, PyHC chat has all the smarts of GPT-4. So in this answer, I'm expecting not just PlasmaPy code to calculate alphane speed, but also a scientific explanation of what that is. And look, that's exactly what we get. Alphane speed is the typical propagation speed of magnetic disturbances in a quasi-neutral plasma. You can use the alphane speed function. And now to...
I'm going to pause it real quick to point out, I know the text is small, so I apologize if you can't read that. And the output here is not super pretty because I haven't done anything to like render the markdown or stream in the answers character by character like you normally would. But you will see what that would look like here in just a second.
Show off what repo prompter bot does. We can ask a question involving multiple PyHC packages. I want to download and plot Soho data. Compare and contrast how I do this with both SunPy and PySpeedas. So, when PyHC chat has to consult multiple repos, repo prompter bot's job is to ask the right questions of each one to get the necessary context. You can see its questions to SunPy and PySpeedas right here.
And I'm also going to pause to clarify that part. So I asked the bot how to plot Soho data and to compare and contrast to how to do that with SunPy and PySpeedas. And then right here is repo prompter bot recognizing SunPy and PySpeedas are the repos we have to consult. And it came up with the questions. I'll read them for you. To SunPy, it asked, what are the specific steps and functions in SunPy to download and plot Soho data? And then to PySpeedas, it's asking, how can I download and visualize Soho data using the PySpeedas package? And yeah, they're kind of like asking the same thing, but randomly worded differently. That's just how AI-generated content works.
In a sec, we'll get answers from both of them. And there they are.
You can't read that.
Here's what SunPy had to say. And PySpeedas. Now it's going to condense all this into the final answer that actually gets shown to the user. So let's go ahead and run this code too to make sure it works. Paste it here, remove the markdown, run it. And woohoo! We got it! Just to show you a quick glimpse of where we can take this in the near future, I want to quickly show you Open Interpreter, which I could integrate to actually let PyHC chat run the code that it writes and things like that. So here I'll just tell it to act as PyHC chat. Cool. Then I'll ask it, how do I download a happy dataset? Show me by running code to get the first few rows of one. And now this is what it looks like when GPT-4 is allowed to use my machine as a real dev environment. Not to mention how it looks when we actually stream in the responses and render the markdown nicely. It just confirmed Happy Client is installed. Now it'll go write the code to get a data set. Then it runs the code, and we actually get our data. So this is great, and I'd love to eventually build this into a real chatbot UI on our homepage or something similar. I'm excited about where we'll take it, and now I hope you are too. Thanks for watching.
Woohoo! There you go.
Rerun it
Now,
in...
If I had more time, this would be the part where I would have you all ask questions of the bot and we would see how awesome it is. But we're going to move on from there to talk about next steps. So there was just a quick glimpse at the power of AI for PyHC. So the obvious first step is to incorporate that open interpreter into my, just command line based prototype so that it could actually like stream and look nice. But the next step is actually just to wait, which might seem kind of silly, but with just the amazing pace of AI development, a lot of the rigmarole I'm doing with like retrieval augmented search to just have it understand the GitHub repos might just become moot in the near future. Because already when I built this like right when GPT-4 dropped, because I kind of had that aha moment, like, oh, this would probably work. But it only had a context limit of 8,000 tokens at that point, which was enough for maybe like a few functions copied and pasted into a prompt if they weren't huge functions. And now it's all the way up to 128,000 tokens, which is actually more than enough for a mid-sized repo. You could paste the entire, code base into one prompt and it would be enough to work with it. So one just thing I could try here is to actually simplify some of the helper bots and not even use RAG at all, and just actually give it the whole GitHub repo. And anyway, there's other stuff like that we could do to make this more production ready. At the moment, it's not deployed anywhere. It's in the GitHub, and I'll have a link at the end of this here in a second. But you need an OpenAI account, and you are actually charged for all the token usage yourself when you use this. It doesn't come out to that much, maybe like a few cents per conversation, but that is a barrier to entry that we would like to avoid. Luckily, they're getting cheaper and faster by the day. So again, going back to wait, one of these days, the technology will just catch up with this idea and make my life easier. And we'll deploy it somewhere, probably as like a chatbot on the website. We've got some neat ideas about how to put this in the notebook interface. And I have a couple just GIFs in here that I'll probably skip past, but this is Deep Note. They have a generative AI like magic thing where you can chat with, I think they actually also use GPT-4, and it fills out code cells in a notebook, and that's like super slick. You can have it edit code or even explain code. And if we had just something like that, imagine being able to ask any question about any PyHC package in an environment where you can run the code, and you can also have it like just help you with your heliophysics research, or heck, even write a whole paper inside the Jupyter notebook and publish it as an executable paper. That kind of stuff is actually low-hanging fruit with this technology. And I'm 1 minute over my time, so I'm stopping there. I'll leave this slide up for a while so you can get a link to the YouTube demo if you want, or the GitHub repo in the middle, and you can email me with any questions. And speaking of questions, Barbara was kind enough to offer just maybe 10-ish minutes extra for any questions in the room if people had them, because 15 minutes might not be quite enough. So now I'll ask that question. Is anyone curious about anything that I just showed there?
You said you had a restriction or a limit of 128,000 tokens for the, was that the 4 or 4.0, or are they the same?
They are the same.
Okay.
Yep.
And then the other one was, you said we need an OpenAI account to use this. Is that, and you also said like we have to pay. So is that like if you pay for OpenAI account, then can you use this? I know you don't have a chat like bot yet, but.
Yeah, there's just, if you go to the GitHub repo, there's like one line in a file to paste in your API key. And I did not put my API key in the repo because I'm smart, but you can go clone that yourself, and you can paste in an API key, and then this just Python PyHC chat.py, and then you're off.
Okay.
Yep.
Hi, this is really cool. So you talked about using this for research and even publications. I was wondering if you could talk a little bit about, citing the work, or, if you're pulling from all of these other resources, what that means for scientists.
Yeah,
using.
actually, specifically on the topic of citation, one nice thing about using vector store retrieval instead of just like pre-training the model to know all of this out of the box is that it actually can cite the sources that it's getting its information from. So when it goes and pulls some PlasmaPy code, I can actually know which file from the PlasmaPy repo that it pulled that from. And I'm not currently displaying that in the output there, but there's a flag I could enable. So it actually would not be very hard at all to have it just include little citation links to every single fact that it spits out, which is good for research. Yeah.
And was there a personal preference as to why you chose GPT instead of like Cloud, Gemini, or just that it was out in the market first?
Oh yeah, it's just my opinion, and I would also more or less assert objective fact at this point that they just have the best model.
Got it.
So I was going to get the best performance from it.
And one last thing was, so you said that you're waiting for, more token limitations to open up and so on. So what is the restriction right now in terms of libraries or packages that are fully capable on your thing?
Yeah, so right now, if you just clone the GitHub repo and did nothing else, I've only given it access to the 7 core PyHC packages, which were the ones that we learned about here at this summer school this week, which is nice and convenient. But yeah, on the topic of waiting for more token limits and that kind of stuff, because you brought up other models, Google's Gemini has actually already been able to reach 10 million tokens with their model, which I believe in that case, I actually probably could just put every single line of code from every PyHC package in one master prompt and say, no, this, and then have the chatbot go off. But unfortunately, Google's bot hallucinates super badly, and I would never put that in front of anyone. So it's like we're almost there. And because you mentioned GPT-4o, it streams in answers 6 times faster than GPT-4 did. So that actually just makes the using it much nicer. So it's like, yeah, all this is happening in the background.
So just to clarify, if we wanted to use this, we would clone the GitHub repo, purchase our own API key from OpenAI,
Yep.
and we should be good to go.
And then you're good to go. Yep.
Do you think our business would pay for OpenAI keys?
That's a good question. I know LASP does not. And we actually considered making an OpenAI API key one of the prizes for yesterday's coding challenge, but we decided that was complicated, so we didn't go there either. Cool. Preston?
I know there's a few different ways that you can run entirely local LLM models that exist. How much worse do you think it would be if I just replaced all the OpenAI API calls to with a local LLM with the same prompts? Do you think that would work at all?
I mean, I think there's a decent chance it would work at all. Yeah.
Okay.
One benefit of the retrieval thing is how I compared it to short-term memory. It's
Mhm.
actually they're much less prone to hallucinating facts if you've just told it the code like right there in a prompt. And actually, it would be a one-liner change in the code base to swap out GPT-4 for your favorite local model like Llama or something. So if you have that on your computer, it's a pretty easy thing to do.
Cool.
Yeah.
2 things. One, for those who are not very familiar with AI ML, what does hallucinating mean?
Oh, yes, I should clarify that. That's just when it says a statement and it's false, pretty much.
Cool. I'll let you get your question, then I'll ask my next one.
On that topic, I assume that while you were building this and trying it out, you asked it many questions. Did
Yeah.
you notice with your committee of experts technique that you had that you got any hallucinated answers? And now in the version that you've published on GitHub, what do you think the rate of that is?
Yeah, if I had to guess, maybe 90 to 95% of what it says is true, which is, I think, pretty good, but also, that's a caveat there you have to understand. But it's always close though. It would be things like, I would ask it to download me a happy data set and it would get everything right, but it would spell the data set name wrong or, little stuff like that.
Are there plans to get this at some point on our website for beta users to test it out?
I would hope so, yes. One other nice thing about GPT-4o that was released recently is not only is it smarter and faster, but it's also cheaper. So just this kind of stuff is cost is probably the biggest prohibitive thing from us actually deploying it onto the website right now. We've had conversations with Brian, our funding dude, to maybe get a small grant of $500 or something and just throw it up and see if people use it and monitor what kind of questions they're asking and that kind of stuff. The $500 would stretch much further now if I use the newest model. So it's something we could look into in the really near future, actually. It's probably just about ready for that. It's just, do we want to spend the time doing it versus other stuff?
did you use this to create the challenge ladder yesterday?
I definitely used it to help me come up with the coding solutions. Yes, I did. And in fact, I'm definitely the #1 user of this right now because I got so excited about building this because it can do a lot of my job as PyHC's tech lead. And so just in my day-to-day, I don't really understand the PyHC packages all that well because I'm not a heliophysicist. So I have actually been leaning on this to like get that work done.
Just wanted to follow up on the hallucination thing based on what you had shown us earlier. I don't think we saw anything come out of this that would lead you down a really bad path. Like usually it would either be fairly evident that it was wrong, and even then it would kind of get you looking in the right direction. So I wouldn't take this as the final word, but it's really great for the I have no idea what the heck to do. Where do I start in the documentation?
Yeah. And I'm noting that we're about 10 minutes over, so we got time for like a couple more questions, but I should probably start wrapping up pretty soon. Yeah.
So I haven't looked too much into Copilot, but Copilot seems to be a bit more free for everyday users. Is there a way to potentially use that as a way to get a cheap beta version out for people to try out or even like install locally somehow?
Yep, I've wanted to do that. I don't really think it's possible right now because GitHub Copilot doesn't have like an API to access Copilot. You have to actually be using the product itself.
Right.
But that's one other example of there are businesses out there that are trying to solve the understanding code bases problem. So if they even just got better and then put an API key out there for you to use, I might not even have to build PyHC chat anymore. So.
Yeah, I wonder if you could also find like some startups that you could like partner with to see if they'd be willing to give you like a free license to demo it and say like, hey, look, we work with NASA or whatever.
I did get on support with Microsoft at one point, and including NASA in my email, I think did add some weight and got them to respond faster, which was pretty cool. Because Microsoft does offer some limited support for people who are trying to build enterprise chatbots with GPT, but yeah, limited.
You have an online question. What's the monthly cost of GPT-4?
The monthly cost of GPT-4 is $20 a month.
There you go.
Yep. And do we have anything else online? Nope. Okay, maybe one last question, but if we don't have one, then I'll cede it over to the other people who are talking today. Going once? Going twice? Okay, cool. Well, thank you all so much.
Thanks, Sean. All right, Barbara, I'm pretty sure I saw you online. You are up.
Hi, everyone.
Hi, Barbara.
Barbara.
Great. And I think I heard Nat Matthews' voice earlier. They're going to be in the room, and Nat has volunteered to kind of be my local ear fly on the wall or ear to the ground or just person in the room to help me make sure that things are going well. I do have a separate screen up for the chat so I can see the chat. And I would invite especially people like Nat and Julie and Sean. I'm very happy to hear comments and things like that because I want everyone to understand this, and also because I've had the internet drop out and I'm just talking to my computer screen for a while. So a little bit of interaction means that there's actually people hearing me, which is good. So it's a real privilege to be able to do this. I was very happy for the opportunity to, sorry?
Sorry, I forgot my mic was still on.
Wasn't
trying to talk at you.
Oh, okay. All right. I'm grateful. We're grateful for the opportunity to really beef up some of our machine learning training materials, because these are it's fun, it's interesting. And I'm so glad that Sean was able to give a demo. Generative AI is really in the getting a lot of attention now for very good reason. It's tremendously useful, performs well, and if you haven't already, it is so wonderful for coding. Like I put this, the most common thing I think I put, well, the two most common things I put into ChatGPT are, can you say this and make me sound smarter? Because I'll be trying to like write a professional email and I just don't have the bandwidth to phrase it in a professional way. And the other one is why isn't this working? Look at this code, tell me, make it better. And it'll say, oh, because, you know, this is what you did wrong, or there's an extra space here or something like that. And it's really handy to figure out what I've, because I'm a very, very sloppy coder. So I tend to focus on machine learning. There are some people that say, well, you say AI, you say machine learning, that's just AI. And it's not really so much about the classic definition. It really has to do with the connotation. AI is even, I mean, with people that are even, I think should know better, people will use it just for something that's just complicated. I mean, it's what they used to call witchcraft, and now they just say, oh, if it's complicated, I don't understand it, it's AI. And it's not necessarily. There is a formal, it does have to have some decision autonomy built into the model in order for it to be AI. Just because, there's a lot of things that are extremely complicated models, but they do not have any autonomy in the way that they implement their decisions. They're not AI. They're just complicated. All right. So, I'm going to do this lecture from a standpoint of, and I hope that this was helpful. A lot of you are pretty good at coding, but there are a lot of mistakes that people will make. And having refereed, I can't even tell you how many machine learning papers I've been through. And there's a lot of very, very, very common mistakes that people make because they're like, I'm good at computers, therefore I should be able to write a scientific paper on this. And I like to focus on machine learning as a topic because as opposed to AI, machine learning does seem to have the context of having a discrete set of input data and statistics and some sort of well-defined task, something you want it to do. And so it does have the connotation of numerics, data, and the performance that you expect out of it. Whereas AI is such a large and all-encompassing term that I'm not quite ready to really say I do AI. So I'm going to share my screen, and I have to apologize to y'all. I've been editing the repository, and it's behind schedule. So I posted a link. Here is the most recent version of the repository. I didn't do a commit this morning because I didn't want to drive Sean and Julie crazy into yet again reconciling all of my little DS store files that appear everywhere because I'm working on a Mac. So, but the code that you have on Helio Cloud in the PyHC repository, that is the same. The only thing that's changed is the text. And so what I'm going to do is I'm going to be working from this link that I put in the chat, but you're fine if you just follow along in the text. If you follow on in the current version. All right. So.
Excuse me,
What?
Barbara.
Oh, yeah. Sorry.
Yeah. I wanted to point out for everyone there, in case you didn't catch that, there have been a couple updates to the repo for her materials here. So like we did a git pull yesterday and the day before, please go through now and do a git pull in your summer school 24 repo before we continue. And if you want help with that again, I can come around and show you how to do that.
Let me see. I'm gonna try to find where is, I don't know how to hide this meeting control thing and it's driving me batty. Yes. So please go and update the repository if you haven't already. So pull latest changes. It's this little cloud button right here. So I apologize for that, everyone. Just reality hits. I got 2 big proposals due today, and I'm giving a talk at a sci-fi con on Sunday. Just schedules, fun. Anyways, while you're doing that, machine learning is generally recognized as a subset of artificial intelligence. And I'm so glad again that we got to talk about one of the descendants of natural language processing and generative AI. And I know that the chatbot you'll find it extremely helpful, because I do. Every chatbot that has been deployed properly has been extremely helpful in getting me to the things that I need quickly. The branch of machine learning in AI is kind of focused on a smaller class of problems. And again, they have to do with the way input data and output, training to have a specific output or response or behavior in machine learning. So, and most people know that machine learning at least can be used for automating and streamlining tasks that can be arduous for humans. But it's much more than that. Let me just here, I'll bump up there we go, that's better. I think, okay, now I can see the screen better. I hope you guys can too. But machine learning is a lot more than that. And the thing that I think about is a lot of people think about machine learning as a way you can, it's a tool. It's something that can, do complicated things. I really think of machine learning as an augmentation of, for something that helps you as a human access knowledge and information more effectively. So one of the great things about machine learning is that it can allow data to speak for itself, meaning that you can explore the data, find different representations, find higher level relationships, and find new representations, your data set that can bring valuable information to light. If you keep on applying the same questions to your data, you're going to get answers in the context of that question. Whereas I believe that in heliophysics data, there are tremendous, tremendous discoveries waiting for us if we allow the data to speak for itself and really perform proper analysis of the different types of representations and the different organizational properties that our data has, that our data exhibits. So machine learning has become really common because of an AI, because there's a lot more data, the volume and accessibility of data, combined with growth in computational capabilities. Of course, there was open source and software environments. It would be so hard to do what we do in our field without the PyHC community. But there are 2 other things. If you read about this, it's really interesting how much we are learning about ourselves, how information is derived from data. And I always say knowledge is information in context. And so information can just be any organizational property of the data. And it might not be useful. But when that information gains context and is related to other information and other knowledge, it becomes part of our knowledge base. And so part of this is in the form of advanced visualization and data representation. The old stodgy ways, look at a picture, make a movie, make a line graph. Those are tried and true, but there's information and there's knowledge that does not yield to those types of representations. And so having an arsenal of excellent ways to view and represent data can open you up to new discoveries and new knowledge. And the growth of machine learning is part of the growth of data science in general. Now, people talk about, and I do this, I think a lot of people, 10 years ago, we would say data science, and a lot of people wouldn't really understand what we meant. Now people are getting more familiar with what we mean by data science. So data science is really, if you look up data science, there's lots of different definitions, but almost all of them agree on the relationship. It's really, and I think the first one is from Drew Conway. I think it's this was almost a joking one, but it was this is borne out over time. It's really the relationship between substantive expertise, or in our case, scientific knowledge. How well do you know the behavior of a plasma, the structure of a magnetic field? How well do you know how these photons are assembled into spectra to analyze? And then there's, of course, hacking skills, the code, computation. How do you, implement and compute these things? But the one thing that is essential to this is mathematics and statistics independent of the computation. Really good machine learning studies take advantage of higher order statistics as well as just simply computation. And so what you get is you kind of need all three of these to be good at machine learning, and certainly good in our field of heliophysics at data science. So you want to have, now, if you're lucky, all of these exist in the same brain. That's not always true. So what some of the best groups in our field have at machine learning consist of partnerships. Like with Sean, we have someone who really knows the code and also does have a decent knowledge of actually how information is contained in data in the first place. And Sean works with the providers of the packages to integrate this together into useful PyHC packages. So, and it's nice if it's all in the same brain, because then you know what you know and you know what you don't know usually. It's a little harder when you're working with people, but I believe that as these things get more sophisticated, it's harder and harder for one person to do it, and you're limiting yourself if you don't find partners. So don't be afraid. If you really know one area and you're not sure about the others, it's an opportunity to find someone and make a partnership and figure out they probably need more help and guidance in the understanding the science, and they can really supercharge your research. So let's go a little bit. Is everybody okay? Any grunts? Hello?
Looks like the room's doing all right.
Okay, all right, great. All right, so what are the types of machine learning? I'm going to get into a lot of models later, but there's a couple of general classes. Really, I mean, it's largely two. They're called supervised and unsupervised. Sometimes there's a third category. It's called reinforcement learning. And really, that reinforcement learning is sort of a subset of supervised learning. So supervised learning is useful when you know what you want, and you just need provide examples to the model to do it for you. So what you have is you're like, I'm going to show this model a bunch of pictures of apples, and I'm going to tell the model these are apples. And then what you want to do is then in the future, when you show the model a picture of an apple that you haven't told it it's an apple, you're just going to show it a picture and you say, is it an apple? And the model will say, well, it seems to be similar to all the apples you've shown me before, so I'm going to say it's an apple. Part of this is, which is really important, if you can imagine, is you have to have lots of examples of things that aren't apples, and certainly a lot of examples of things that are close to apples, like peaches. So that the model will get better at saying, okay, because if I only show it apples and you say, is it an apple? It's going to say everything's an apple because it doesn't know what's not an apple. And so you can train it, and then that's what a supervised learning model typically does. An unsupervised learning model, what you do is you put in a bunch of stuff and you say, hey, here's a bunch of stuff. Do me a favor. Do you see any similarities? Just look at the properties of this data, and can you put this into some, can you reorganize this data in a way that has lower entropy, has more organizational, has better organizational similarities in nearest neighbors, yada, yada, yada. And so what you do, and this is what's called unsupervised learning, because I have not told the model what the answer is. I have not said, this is an apple. What I've done is I've said, I just, go ahead and see what, and find a new organization of this data that you think that might be better than this one. And so supervised learning has kind of two general areas. There's classification, and this is a classification problem. I'm saying, is it an apple or isn't it? And so supposed to, and the model's supposed to say yes or no. It's supposed to put in and say, this is a classification problem. Another one is regression, which is something that pretty much everyone's done. You measured temperature as a function of time, and then, in school, and then you drew a line, the temperature, and you said, oh, okay, now let's see, is there a relationship over time of the temperature? And that's so these line fits, or these relationships between variables are generally called under this as regression. And a lot of people are surprised to find out that they might have already done machine learning and didn't know it. Because sometimes when you just do an XY fit and you say, hey, can you give me a least squares fit with a standard deviation? Some of these are directly solved, and some of these are iteratively solved. And the iterative solving it's a least squares fit. You have not told it what the answer is. What you've told it is you've told it how to solve the problem. And so a least squares fit is a common type of regression, and it might even, depending on the function you're using, be used in a technically machine learning thing, because what it does is it guesses and it says, nah, that looks terrible, I'm going to try again. And then it gives you an answer that best fits your criterion, rather than giving and exactly solving for a matrix. So, and I'll get into that a little bit later if that didn't make sense, don't worry. And so this XY relationship is often and so yeah, so it's usually or some people call it an XY plot, where there's the independent variable, which is maybe time, and the dependent variable, which is the thing that is changing with time. And this has heritage in the way that models are implemented. You'll often see that the X is the input, which usually we'll call this vector here that we put, or this array that we put into the model. We will have a set of images and a set of labels, and those will be called X. And the prediction is what we call Y. Now, this will be X. This will be X, and the annotations that we're comparing to the predictions, that is Y. And so you want to predict, you want to say, what is this as a function of this? So this is X, this is Y, and what they're trying to do is update Y to come up with a Y function that best approximates the actual answers, or the Y values. So that's a weird little thing, a heritage there. Unsupervised learning looks for relationships in or organizational structure in a data set. It's one of the most fun things about machine learning, because if you do it well, you can really find interesting ways of re-representing your data. And so the model is not given examples of a correct answer to train it. It uses it uses a general criterion or performance measure or cost function to find the best way to reorganize the data. And so you might want to say, you might have a cost function that looks at you look to minimize the differences within the sets. So you might want to say, okay, if one looks significantly different, it has a larger penalty than if within each set it's the same. And it tries different organizations of these data until they find one that minimizes the difference within the sets. And that's an example of using a performance measure that the model is trying to meet. And a common case of supervised learning in this case is clustering. Another case of unsupervised learning is dimensionality reduction, where the model tries to find a lower dimensional representation of the data that preserves its essential structure. And humans do dimensionality reduction all the time. There are 8 billion people in the world, and you cannot learn everything about people. And so what you do is, whenever you meet a new person, is you focus on a couple of variables. And that's something that we'll do, that we, is this someone that I know from, am I meeting them from work? Are they someone that might know more about technical things? You know, these dimensions that whereas if they like cheese or not, may not come, you know, if that's a variable that that person has, you might not need it to be able to just sit and have a conversation with them at a, you know, at a meeting. Anyways, so we do dimensionality reduction all the time. And this is a common thing that people do because there's so much data out there. And two things that dimensionality reduction does is it can reduce the amount of data to make it tractable by by finding a lower dimensionality reduction of the data. You know, so if you have large volumes, it's not uncommon to explore dimensionality reduction as a way to make your data set more manageable. Another cool thing about dimensionality reduction is you can tease out really important relationships in there. You can see whether there are things that are completely random. Like the third digit of your a social security number or of a or a passport number, you know. That is a variable that, you know, you could collect, but does that have any value? If you reorganize the data in any way, does it give you any information? Does it correlate with anything else? No, it does not. And so if you do real dimensionality exploration, you can find real properties that correlate in sometimes surprising ways. So you can, rather than just focusing on, you know, velocity versus time and magnetic field, you can really look into some higher order connections. All right. By the way, I was going to give everyone maybe a break at a brief break at 10:30. Does that sound good, Julie? Just a little bit of a breather.
Yeah, that sounds great. You're
Okay.
saying
Yeah,
10:30 Mountain.
Okay. Yeah, I just want to give everyone, you know, a little bit of a break. So yeah, so there are common applications. I'm not going to get in them too much, but you know, if you go into unsupervised learning, you're going to see clustering and dimensionality reduction. If you look at supervised learning, you're going to find classification and regression as common applications. Now, throughout this entire training thing, you're going to see these examples. For example, so where would you, let's say we have a problem in heliophysics. We're trying to forecast a flare or a geomagnetic storm. Where does that fit in this landscape of machine learning? Let's say I have let's say I have a whole bunch of measurements of the solar wind and I'm trying to predict the magnitude of a geomagnetic storm. Now, it turns out that it could fit in either category. If you have a bunch of measurements of the solar wind, and you also have whether a storm is strong or not, you could do a supervised learning method. You could use regression. You could say, given the solar wind values, I want you to predict what the geomagnetic storm index is. That's standard regression. You could also divide these storms into storm types. And you could say, hey, you know, I would like you to tell me whether a geomagnetic storm, it's a substorm, or if it's got a certain, you know, if it's got a, you know, certain level of radiation belt activity. You could look at those parameters and solar wind parameters and then classify them according to what type of storm properties you'd get. Another thing you could do is you could ask, okay, I have this whole data set. Are there ways, you know, I have solar wind data, I have velocity, I have temperature, I have magnetic field, you know, and here they are. Are they, and we'll see an example later on that says, okay, rather than just treating it like that, is there a way that without me labeling it myself, is there behavior? Are there sets of domains in that multi-dimensional space, that 7-dimensional space, that the solar wind tends to hang out in, like fast speed or shock, you know, and are these things there? And also there are many examples of people using dimensionality reduction for solar wind. For example, Sean was showing an example of how do you compute Alfvén speed. That's pretty nice to have. Instead of being like, okay, I need my velocity, I need my temperature, I need my magnetic field, and so if you combine that into, if you can reduce a lot of that information into a parameter that contains some of that relationship, that's really useful. And that's an example of dimensionality reduction. Finally, reinforcement learning is something that's kind of useful for forecasting. What you're doing is this model is guessing. And the most common example people talk about with reinforcement learning is a self-driving car, an automatic driving car. You have a car and it's driving and you're driving, and you're basically saying yes or no, and it's trying to learn what matters, what information it needs to use, and how does it react to that information in order to predict its future performance in line with what the model is deemed to be positive or beneficial. And this is something, even self-driving cars, you could use in forecasting, because you, as the user, you could be like, okay, it's trying to forecast a storm or a flare, and the user could be like, oh, nope, you needed that flare to be lower. Next time around, do better. And it learns, and it's going through and it's doing that. Let's see, is there a chat? Okay, that was just a smiley. All right, good. All righty, so the next part gets into more of, now we're going to get into actually doing stuff. Do we have any questions on the first section? People still there?
Yeah, we're still here. I was just waiting to see if there was a question.
All right.
Is there any on the other side of the room? Okay, cool. No, keep going.
Great. All right. So I think people used to say that, a lot of people have learned about a definition of AI from the 50s. It was like, it gives the computer's ability to learn without being explicitly programmed. I think I still hear that sometimes, and I don't really like that. I don't like that description, because it really doesn't. It's fuzzy. It doesn't give you really operational understanding. For machine learning, I really prefer this somewhat more recent definition. And it's dense, but it's actually mathematical. It translates directly into the way we implement models. And so you get this, you will get exactly how we do machine learning models. So a computer program is said to learn. In other words, so we want a program to learn and not just perform as we told it to. It's learning from experience, which we're labeling E, with respect to some task T and some performance measure P, if its performance on T, as measured by P, improves with experience E. Now that sounds a little, it's a mouthful, but for me, it's so useful. So E, that's your input data, or X could be from the way we often name the variable. It can be numbers, images, words, sounds. It's just whatever you're given the computer. That's it. And that's what your input is. T, your task. What is your intended output? Do you want to label these things? Do you want to make a decision? Do you want to predict a value? Do you want to say, hey, does this have, are there clusters in here? Can you organize it into groups? T is your task. This is what you're asking the computer to do. This is the intended output. This is the thing the computer is supposed to give you at the end, or the model is supposed to give you at the end. P is the interesting thing. P is the thing that is special about machine learning. It allows the model to decide how to solve the problem instead of having the solution explicitly programmed. So a performance measure is something that says, okay, I want you to minimize the number of wrong answers. That's a very simple performance measure. So if you're trying to show it, get it to label pictures of apples, oranges, and peaches, the performance, you're telling the computer, I want you to get as many right as possible. And you'll be penalized for everyone that you get wrong. And so your goal is to minimize the number of wrong. Let's say, so you might have, so sometimes that's called a loss function or a cost function because you're penalizing incorrect performance. And so what the model does then is it keeps on trying and trying and iterating until it finally thinks, okay, I've gotten the best performance measure. I've reached the part where I'm performing the best. It's rare that it's perfect, but it'll get to the point where it says, I'm not improving. This is the best I can do. And so anyways, and so that more the T, E, T, and P are more clearly explain the key components of machine learning. The other thing I like about using this definition is nearly all AI fails can be traced to any or even all three of these elements. So everything that you could get wrong, usually like it's sometimes it's easy, sometimes it's not. There's an example of where people were trying to train a model to discriminate between wolves and dogs, particularly huskies, which look like wolves. You know, they're big dogs with and and what they did is they went on the internet.
Hey, Barbara.
Get tons and tons of lots and lots of images because you're like, okay, we want to make sure that we have a huge training set. Let's give it thousands of images so it gets really, really good, gets lots of examples. Because there are times when we see a husky, a dog, and we're like, wow, is that a wolf? And so you want to give it lots and lots of examples.
Hey, Barbara.
And it did brilliantly.
Barbara?
Oh, sorry.
Oh, there you go. We have a quick question.
Oh, yeah.
Hi, Barbara. I know you can't see me. This is Ritu. I work with Shay at Stanford.
Hey.
Before you dive more into the next section, I guess, neural networks, I had a quick question on your previous section on supervised, unsupervised. Was that, is it always that, you know, black and white where you have a set of data that you can, like we can label very clearly to help the model to better predict? Or is there sometimes where you have, say, a section of a huge amount of data where some amount of it you can label very effectively to help the model train, and then another segment where you kind of have no idea or you don't want to necessarily label them and let the model handle it? So what is that gray area? Does it happen in the world of ML? And what
I suspect, Ritu, I suspect you know the answer. Which is you know, from even the way you said it, right? Which is that that typically it's pretty rare when you get one that's so gift wrapped that it falls right into the, like, I know exactly what I want from this, and I know exactly what model to use. Rare. So what we'll typically do is I kind of think of it as you're going you often start with the unsupervised learning realm to do things like get rid of unrelated properties, clean it up a little bit, organize a little bit better, take a look at it. And then once you've gotten a little bit better idea of what's in your data and and you might have a specific task you want of it, then you might move it over to supervised learning. But again, supervised learning is only only the case where the supervision is you. You're the person that's saying, this is exactly what I want, and I'm going to grade you on how well you match what I'm saying you need. Whereas in unsupervised learning, you're like, you know, let's see what it does. You know, let's see. I'm grading it on how well it finds a way to reorganize the data for me. Whereas in here, I'm grading it on how well it takes that data and finds direct relationships or classes. So does that make sense? It's again, that's why I don't like to think of I know machine learning is useful as a tool. And if you know exactly what you have a nail and you need the hammer, you're good. The problem is that, you know, I think of data science more as carpentry, where you really need to, an excellent carpenter knows how to use a hammer, right? Knows how to use a drill. But they also have an excellent repertoire of other tools. And if they need those tools, they'll know what those tools do and when you might need to use them. And so, and what steps you apply those tools in. And so if you think of it like carpentry, then if it's an easy problem, if it's all set, oh, the shelf fell off the wall, I got to reattach it. Then you're good. Then you can have that. But if you're like, how am I gonna, I'd like to make some sort of general space in my home that organizes things but doesn't look ugly, and I'm not sure if I want shelves, I'm not sure if I want drawers, I'm not sure if I might want a closet or something like that, and shelves are so hard to build, built-in shelves. I could just have standalone shelves. Anyways, I'm getting kind of off track, but the idea is that the more you have an idea of the range of possible solutions and models that there are, the better you're going to be at when hit with a new type of information. You'll be able to at least understand what you'll be able to do with that data. But again, the coolest stuff is not when you know what you want. The coolest stuff is when you have no idea what's in that data. And so you're going to explore and see what that data tells you. If you let the data talk to you instead of you force the data into some form just to be able to answer a very restricted question, I believe that really opens you up to new exciting things. Almost every decent paper I've ever written has some element of, what on earth is that? Like, I went to do this, I'm like, okay, I'm trying to prove that A is related to B. And I'm like, what is that? Is that C? Like, and then I end up writing these cool papers on something that I didn't even expect to see. And so machine learning, and that's something that you can do regularly just looking at data. But if you can imagine that interesting stuff is hidden in a way that humans don't easily identify it, machine learning can be your pathway to really exciting new relationships. Let's see. So Chuck Woma says, for example, we have different data with similar values, how to control the model. Let's see. Can you clarify that a little bit in the question in the chat? So, I'm thinking, or if I was talking about, maybe this will help. I was talking about the example of training photos to study to determine whether they're wolves or husky dogs. And you can collect 10,000 images, which is great. You have a huge sample. You get a lot of overlap between what a husky and a dog looks like. And the model performed brilliantly, because what the modelers did. Oh, thank you. Oh, good. I'm glad I answered that. What the modelers did, and they got perfect performance. But what they did is the model was not asked to distinguish between the animals in the photos. It was asked to distinguish whether the photo had a husky or a wolf in it. Can anyone guess what went wrong? And if I already know the answer, then this is a common example. But does anyone have any idea what went wrong when these people grabbed a bunch of pictures off the internet and got perfect performance, almost wolf versus husky?
We have one guess.
Oh, yes.
I think it was the background. So the wolves, or was it the wolves had a snowy background compared to the huskies have like grass and stuff?
Yeah, yes, exactly. So what it was, you did not ask the model. You gave it data. You did not ask the model to distinguish between the animals. What you did is you asked to distinguish the photos. And it turns out people don't typically hug wolves. They don't normally have close-ups of wolves with their tongue hanging out looking all happy. Wolves don't usually sit on couches with people. And huskies usually are not far away. The grainy photos from far away in snow, all alone without anything near it. And so it did very well because of the context of the photo. And so that's the problem. And so what you did is you gave it a large data set, and you did poorly because you your data set is not representative of what you wanted to use it for, because what they did want to use it for was an automated webcam that took the photo and could tell which was a wolf and which was a dog. So it'd be the exact same photo, type of photo, the same context. They wanted it to look and see, you know, so the input data did not reflect you know, because they wanted thousands of images to train on, and they only had a couple of the webcam photos. They're like, not enough data to train on, let's go get more. All right, so the input data was not representative of the data they're going to use it on. The output, the task they gave it, was, is the photo a photo of a dog or a wolf, instead of, is the animal in the photo a dog or a wolf? So that was their task. And also their performance measure was wrong, because it was rewarded for picking picking the photo, the labeling the photo correctly, and it wasn't rewarded for anything about the dog. Now, this is the cool thing about explainable, interpretable AI. I'll get into a little bit, but you can catch that problem real quick, because a lot of people think of machine learning as magic. Every single model in machine learning has associated interpretability tools that you can use. Some are harder, some are harder to use, but either way, you can always trace through and find out why the model made a decision. And so if you do something, what they call saliency, which tells you what aspect of the photos had the biggest influence on the decision of the model. So what it does is it just goes and you hold up the photo and you trace the different pixels in that photo as as it propagates through the model, and see which ones have the largest influence on the decision. They found out that the dogs had the least influence of anything. Everything around it had. And so you can catch it, you don't have to deploy it, you can fix it. Anyways, so that's a thing. And I believe that it's very important to always build from the start interpretability and explainability into the way you do things. So you can always make sure that what you told the computer to do and what the computer did are the same thing. So yeah, so again, and it's fun. I've always wanted to just give a whole lecture on AI fails, because those are they're hilarious, and you can always, and sometimes it's not really clear where it comes from at first, and then you go, oh, that. Ugh. All right. So I'll get a little bit later. I have a whole thing on the data cycle, but the first stage of machine learning is collecting the data. It's often called data prep, data wrangling. It's usually the longest stage. It takes a lot of time to really get that data in a form where you can sanely have a computer give you some real results. The second stage cannot be skipped, data exploration. You must get to know your data. You must look at it. You must understand its behavior, its basic statistics, and so that you can understand which models may work best. You may understand, and also you will have to see if the data is sufficient to address the problem. You may not have proper statistic coverage of something, and you have to explore your data. You have to go through and really examine it and understand your data well in a classical sense. Look at it, plot it, do distributions, run movies, plot subsets, anything you can do to the data to give you more clarity. The better you know the data, the better you're going to be at picking a model. Because choosing a model requires both careful consideration of the data and the task. So sometimes you want to explicitly consider the performance measure too, or sometimes the performance measure is really inherent in the model and you don't have to worry about that. Once you've chosen the candidate model, you train it. This stage is called, in a typical way that you train a model is called the train test validation test split. So in this case, usually most of the data is for the training and fit of the model. In other words, these are pictures of apples where you're saying, and then there's labels, and you're saying, okay, this is a picture of an apple, this is a peach, this is a pear. This is the model is trying its best to go through and say, hey, okay, that's an apple, that's a peach, and it's iterating. What it does is it usually creates what they call a hypothesis, and then it looks and sees. And so the first hypothesis is often random. It's like, I'm just going to randomly assign apple, peach, pear, apple, peach, pear, apple, peach, pear in the whole data set and see how I do. Okay, I got 1/3 correct. And then it goes through and it looks and it says, okay, the ones that were wrong, what direction, how was I off? And then it goes back and and then it goes back and makes another guess. It's like, okay, now I was 40% correct instead of 33%. What things were fixed, weren't, and it goes back and it iterates and it improves the performance until it gets the best possible one that it thinks it can get. But let's say you're trying to get a model to fit these data points. These are the data points as a function of time. And you say, hey, I want a model that covers these points very well. And you don't give it much restriction. Well, here what you get is, this is what they're calling overfitting, or this is a high variance model, meaning that it's done a great job of hitting the data points, but it's not going to be useful in the future. When you use this model to predict what this data point would be right here, where my cursor is, I know it's not so easy to see, but right there, it's going to predict that it's down here, but it's probably going to be more in here. So what you need to do is if you just tell it, nail this data set that I've trained on, then you might not get much value in the future performance. So what you can do is then you can say, okay, I need you to be somewhat simple. I need to have, something that there are parts of the model where they play against each other, where you're maximizing the accuracy, but you're actually trying to minimize the amount of parameters used to define the model. And so this is a high bias one or underfitted model, where I've said, okay, it's done its best, but it doesn't have enough parameters to really capture. And so there's like a sweet spot between the two. And so what you typically do is you have different data sets that are used to play against each other. You have your training set, which works to improve the performance. And then you have a validation set that goes and says, okay, this is what your prediction is, but now I'm going to send in new data that's part of this distribution, but was not part of the training set. And you did terrible. And so the validation set says, nope, you're too try again. And then it goes back and the validation, and then so the retrains and makes another guess. Okay, you said it was this looks like there's too many variables. How about this? There's 2 variables in this model, too low. And then it iterates between the 2 until they get a good fit. So you're trying to get the interplay between these things. And that's typically what you do when you split, when you're preparing your data, is you have to, depending on the model and how it treats the data, you do have to consider which are the data are you going to teach, and then which are you going to use the model, and which of the data are you going to hold completely separate to evaluate how well it does. And that's your testing set. You do not talk about how well the model works on this. What you do is you evaluate how well the model works on the data that's not in this distribution, but that wasn't used to train the model. So anyways, this model can so it's an interplay between the two. You have to strike a balance. And so that's kind of how machine learning really simply works. You have a lot of you have your T, P, and E, and then you have the way that the model works to take that performance measure and optimize it in a way that's useful for future use. Let's see. So and I wanted to get a little bit more, I know it's been a while, but I want to get a little bit more into specific models, because then we'll get into the code and we'll be running some of these models and you'll be playing with some of these things. One of the things is typically what happens is the training set, you're going through and you are working on the little elements of the model. It might be the weights, there might be different weighting factors, there might be little regular parameters in the model. And then that's what usually the main set does. And then a validation set, before you test it, can often say it looks at the hyperparameters. For example, how many orders in a polynomial are you allowed to use? And so what the then or hyperparameters are guiding properties of the model. And we'll get into that, don't worry about it. But it's kind of how the model runs, rather than the actual fine numbers that are inside the model. These are guiding numbers. And what it does is it works to find the right hyperparameters so that when the model is training, it can do it's the best job it can do. There are throughout all the materials, I do have, I think, really, really good references. I like towards data science, Medium, KD Nuggets. There are several sites that do an excellent job of explaining data science and things, and they're top notch. And so if you want to dig into them a little bit more, you can see the different types of models. But let me just quickly go through in a little more detail so that when we do our exercises, you'll see what we're doing. Regression, linear regression is one of the first types of models you learn. It just X versus Y predicts the value of the unknown data based on the input of the known data. And they're very useful if you want to understand the relationship or correlation between different variables. Again, an X versus Y fit or something as a function of time is a form of linear regression. But there are many more regression models. There can be many, there's unlimited dimensionality to these models. You can have as many dimensions as you want. They do not have to simply be X versus Y. And regression can model both discontinuous and discrete variables. Logistic regression takes input variables and models the probability of a set of possible outcomes. And so you could be a common logistic regression is a prediction of a yes or no outcome. Will there be a solar flare? Will there be a geometric storm? You could do linear regression and say, what is the magnitude of the flare over the storm? Or you could just have logistic regression and say, yes or no. There are strengths to both of those cases. It depends on what you're trying to do with it. A lot of times people have tried both to see which one works better. There may not be enough robust information to predict the strength of a flare, but you could say, will there be a solar flare above this magnitude? If you change it into a yes or no question, then there might be enough statistics to be able to answer it. All right, we will do our first exercise is on dimensionality reduction and clustering. That's fun. Again, I like letting data tell you. I like letting data tell you what's in it first. So dimensionality reduction and clustering are common unsupervised approaches. You're just trying to find different representations of the data. You might want insight. You want utility. You might want manageability. So if you have a complicated data set and you want to turn it into something more manageable, these models can be very useful. So dimensionality reduction looks to transform things into fewer dimensions, usually 2 or 3 dimensions, because that's kind of the data that humans are comfortable working with. But you're trying to do it without destroying useful statistical properties. And so let's say, like I was saying earlier, a common dimension reduction problem in heliophysics is taking plasma velocity and magnetic field. You have 3 dimensions of velocity, 3 dimensions of magnetic field. But if you align it, if you take that velocity and rather than worrying about X, Y, and Z in some arbitrary coordinate system, you can reproject them into a dominant, a prevailing magnetic field direction system. And then you have fluctuations transverse and the velocity, whether it's normal or transverse. And that brings you down from 6 coordinates to 2 from each of the parameters. And that can be very useful to have. However, it's often not clear what coordinates would serve best for a particular data set. So unsupervised models can help with the most information preserving transformations. Clustering is also useful again when you're trying to see if there are groups in the data and you're not sure how these groups are defined. There are lots of clustering models, but sometimes the best way to determine it is just try them out and see what they do. There's another really useful thing about clustering, which is if you're trying to do regression and you want to see if your parameter space is well sampled. If you want to make sure that what the information that you're giving the computer is well sampled in your entire parameter space, you know, you can, let's say it's a 7-dimensional parameter space. You can plot, or you can ask a separate and unsupervised thing and saying, hey, is this a nicely sampled parameter space? Or are there parts of this parameter space that are overrepresented in the n-dimensional volume of data? That can be very useful. So again, I like to start with unsupervised unsupervised exploration, even if I do want a supervised result, because unsupervised can tell you whether there's surprises hiding in your data. This is a Kaggle.com result article that I think is quite good. There's tons of them out there, but there's ones I thought I would point you if you have more questions. Can really describe several models. In particular, there's just some, to be honest, clustering models are my favorite. I absolutely love to see especially ones where if you look for something like UMaps and things where they're doing transformations that are not linear. And they are just all over the place, and they're and ways of completely re-representing the data in a way that pulls things out. They are wonderful, and we did a study on that to apply that to icy moon data, where you don't know what we're going to see, and we're not going to be able to send it down. And so, if you can reorganize that data into clusters, you can say this is normal stuff and this is weird stuff. Send the weird stuff down. That's the fun. I love that stuff. That's really cool. So our first exercise is going to focus on a simple k-means model. And what I'm going to do is, this is a very, very, very simple clustering model. And I'm going to bring you over to the, if you can go into the repository. If you go into summer school and then AI ML tutorial, and then course materials. If you go here, you will see clustering simple. And so if you can please bring that up, that is the example that we are going to be working with. Let's see. Can you go? All right, I'm going to try to get this screen nice and well behaved without it being too irritating. Let's see. All right. So what I'm going to do is I'm going to walk you through this, and then we're going to take a break, and then you guys can do a little bit of you can play with the model a little bit. Let's see. Dean Thomas says, do AI/ML researchers use statistical metrics? Let's see, and then to decide whether they're overfitting to help select the best model. Yes, that is it is. After a while, you get a real intuition. The metrics, if you understand the distribution you're dealing with and the way that distribution is going to propagate through your model into your result, then often it very clearly can give you a metric that is very useful. And other times, not so much. You got to try different ones. It's really, and the landscape of the types of models out there are insane. There are some very good resources on what kind of basic statistical performance measures that you can implement. And it is, but you know, even when you think it's good, sometimes I end up switching it. So it's again, it's a lot more work than you think it is. It's not just, you know, put in the stuff and crank it away. It's these things are very iterative. If I get to it, I will show you we had a process engineer come and study some published results in machine learning in our field in heliophysics and earth science. It was the group. And he captured the flow diagram of how it worked. And it was insane. I mean, like the amount of times that we went back and around into, oh, now we need more data. Okay, now I'm going to go in the model. Wait, this model, it's still not quite right. Oh, I see now. Now I need to go. It turns out this model doesn't appropriately treat this, treat this discontinuity right or something like that. I got to swap out the model. Okay, this model needs even more data. I'm going to go back and now I don't have enough. I don't have enough negative cases. I got to go back for that because this one doesn't like, it likes even sampling. It doesn't like uneven distributions. And you go, and it was the process engineer could not fit even our simplest effort onto a single page. It was all of them. And so it's all these aspects are, people think, you make the data and then you put it in the model and you train the model and you look at the result. And it's like anything else. It's really an art. It's more carpentry and less just direct follow the instructions. Especially in science. Because science, you're trying to find or do something someone hasn't done before. If you're trying to publish something, like you don't write a paper about something that people already know. Or something that they've already done. It's got to be something new. There's got to be some reason when you write the paper that the world needs to know about this, which means that if you're in uncharted territory. And so in science in particular, it's challenging. But it's, again, the people who stop trying to force the problem and let the data speak for itself are the ones that in general are the most successful practitioners. They don't make as many mistakes, and they also open themselves to much greater discovery. So I hope that makes sense. Again, it just is, yeah. And I should also say, there's no right way to do something. Data science is really about just finding the most valuable way to re-represent your data, or not even the most valuable, a valuable way. Here, I've done this. Is this better? Okay, I like this better. Good. This has more information. I've learned something. This is useful. You're just trying to manipulate and re-represent or do something with the data that is valuable. And so you don't, and you quit when you either think you've satisfied an objective criterion that you set forth, or you're just sick of working on it and you want to work on something else. Often, you quit because you're like, that's pretty good. Okay, I think I can stop here. But you could keep going if you wanted to. Either way, so clustering is a very common problem. It's a common approach to unlabeled data, and it's a good place to start machine learning. And so what we're going to do is we are going to have a very simple distribution. In this case, the three elements of the model are going to be a collection of data points in 2D space. The task is, we're going to specify a number of clusters, and we're going to identify the way that the data points are clusters. And our cost function is we're going to minimize the total distances between the points and the centroid that the model has associated them with. So this is a nice thing provided to me by Michael Kirk. I was saying, so this is how k-means works. And so k's are like clusters in the data, and you're talking about the mean, what you're doing. So here's your data set. That's actually, you guys can't see that very well. Let me expand this. Let's say now we say we want 4 clusters. And so our first guess is going to be these 4 points. And then, so what it does is the next step is it goes through, and for each point in the entire distribution, it figures out where the nearest initial centroid is. So it's got actually there. And so you notice right here, this little one right here, didn't get anything. And so you're like, how's this model going to improve? Because this one got all of them, this one got these, this one got these, this one got none. But what you do with k-means is then you say, okay, now I've assigned each point in this entire distribution has been assigned to one of these 4 groups. Now I'm going to update the locations of these groups. I'm going to move my second guess of the centroids of the 4 groups to be the mean value of all the points that were assigned to it. And so now I've done this. I have 4 groups. Each of them moved over to the mean value. And I'm like, oh, okay, let's do this again. Oh, look at this. Now this little point here is getting some values in its group because these ones ended up moving so far away. So you keep on, you do that, you do the recomputation, you adjust. Then you do the recomputation, you adjust, recompute, adjust. And then finally, after a while, you can do this 100 times. And but it's going to give you the same value because every time you update, it's already at the mean value of all the clusters that are in there. And so it's not going to update because it doesn't move the point. So that's how this works. It's really handy. And it's as simple as they come. And it's nice too because we'll use a software package in a little bit. But we don't want to quite use the software package yet. What we want to do is have it be something that you could run yourself. So we choose the number of centroids. Let's go 3. Let's see. And then what we do is we generate a distribution. And so if you just go through, I think you guys probably have had to pip install a couple of things or make sure, but if you don't have, you guys have used NumPy and Matplotlib plenty. And so it should work. If not, ping Sean and people like that too, or Nat or Julie to make sure you're getting things running. So what we do is we create a distribution. We're just having, and the distribution is defined by a couple of things. Let me just pop down here and show you the distribution. There's a number of points in the distribution. There is the amplitude, meaning how large the spread in the distribution is, and then it generates a bunch of random values. And then finally, it applies an offset. And so it says, okay, so this one's kind of clustered around here, this one's around here, this one's around here. Like we have offsets in these distributions. So we have 3 distinct distributions that are in here. So this is what that's doing. And then what it does is then it takes away, it concatenates all 3 of the original distributions. So you lose any information. You do not propagate any information about which distribution it was originally generated in. So now we've concatenated it. And here we have there, and then what we've done now is we have labeled them all with 0. We've added an extra, so our data set is XY coordinate, and we've added, and then there's a 0 label, meaning that they're all assigned to the first cluster to start the iteration. Then we do 3 initial centroid locations. In this case, because if we chose exactly the same point in all 3 of the centroids, because of the way this works, the model works, it would never update because if they were all exactly the same location. So what we've done is just you could either generate a random set of points for your initial guesses for your centroids, or in this case, we just popped them in kind of in the middle. And then you can do that. And then finally, you run through, the k-means function is exactly what that video just showed you. What it does is it goes through in that range, I'm going through and I'm computing the distance to each of those clusters, the centroids. And then that data point is then assigned to the cluster that's the minimum distance from it. And then we go through, and then we go through, we assign the clusters there. And then this is the part where now we are taking the average of those clusters and moving the centroids closer, inching them closer. Recomputing the distances and doing this, and you iterate this until you get, and then in this case, the terminator is, let's see. Yeah, so this is going to run until the cost function, the sum of the distances this is, so the sum of the distances does not change. So from each consecutive step, the distances don't change, which means the centroids haven't moved. And so it's going to run until then. And then you plot your final results and you see, look at that. Our 3 centroids landed pretty well right in the middle of our distributions, which is nice. So these are, and what I've also done, so so we have the big green, big red, and big blue are the actual centroids of the distribution, statistical centroids, and for as generated by the model. And these are the ones that because these statistics are not fully sampled, these are the ones, these black ones are the ones that are let's see. No, yeah, the black ones are the initial centroids, and the red, yellow, and green dots are the ones that were computed by the model. And again, because they're not perfect distributions. And so we can compare the final results. We can see that they're pretty close. And I have a bunch of exploration exercises you can go through to see, to play with the values, to see what happens if you have better statistics. You could modify it to make it a 3-dimensional distribution rather than a 2-dimensional distribution, see how that does. You could try, the cost function here is simply the sum of the distances. You could try the sum of the squares of the distances if you wanted as your cost function. So there's lots of different things you can look at. But the nice thing about this is not a package. This is just simply a k-means, of simple computation. There are some great examples here of this is a phenomenal textbook. This is the Heliophysics Helio ML machine learning textbook. The great thing about this textbook is that it has papers, actual published papers, research papers in our field that are published with the code along with them. And so this is accompanying the published paper. I think, hopefully this will be less of a thing later on. Hopefully interactive code-driven papers, code-embedded papers become the standard. But the nice thing here is you can go through and you can see how this group, instead of doing simple k-means clustering, used a very cool classification scheme called UMAP, where if they go through and they actually, this isn't the UMAP one. I just clicked on a random one. Sorry. I think is this the UMAP one block? Yeah, I think it is. Let's see. Yeah, there we go. It is. Yeah. Anyways, and so what they've done now is they have a more complicated, but it's a more complicated geometric transform. But look how interesting these clusters end up being. They're concise in the space in this new representation space that they found. So it's very cool. It's very cool the way that they were able to and then there's also some pieces that don't quite fit in there. So anyways, these representations to me are a little bit cooler than the simple k-means representations because they've transformed not just looked not just for similarities in the latent space, the coordinate space, but they found a different coordinate space that works. So if that's good, I think we're going to take a quick break and then you guys can start experimenting with this notebook. Does that sound maybe a 10-minute break? Is that okay?
Sounds good to us.
Okay, let's see. And I'm looking at how's the schedule? I'm supposed to be finishing at
11:45.
11:45. Okay, so we have an hour. All right, that's perfect, actually. Perfect timing. All right, so let's see. Let's take a 10-minute break. Experiment a bit with the notebook. And if you're kind of bored with this, you can go ahead and play with the TensorFlow stuff a little bit later. Okay?
Thanks, Barbara.
Sure. All right, if you can let me share the screen.
So loud. All right, people are filtering back into the room now. Yes, thank you for the reminder, John. For those who are here at our next break, after Barbara is done presenting, we're gonna take a group photo. So just know that. All right, Barbara, you can go. I'll stop sharing.
You should do an online group photo too. Have everybody turn
Ooh.
on the cameras and screen grab.
Ooh, do we wanna do that now? Or do we
Yeah.
wait? Let's do it now. Okay,
Let's do it now. All right, everyone. Everyone was there, camera on.
Show your wonderful, beautiful faces.
I see Liang. Hi. It's good to see you.
For those who are here, camera on.
Camera on. I learned a cool thing. There's Zoom meetings and there's Loomers. Like Zoomers are people who are engaged and Loomers are just people who are logged in. But are really just waiting for their names to be said. So cool. Hi, everyone.
All right. Gonna wait another second for cameras.
Oh,
everyone can face the camera that's on only one side of the room.
Can do
my camera's not on because I'm currently at the other place I'm logged in. In-person people, yes, coming to the other side.
Nice, Sarah.
1 second, we're having.
I have my sons in the background, so
we're having a pilgrimage to the west side of the room at the moment.
Okay.
All right. Anyone else who is still online? The T minus like 10 seconds to turn on your camera, pretty please. We're gonna get a group photo in person at the next break, which is what I was saying while talking. Okay. Are we ready? Are we ready? All right, everyone. My camera's faulty. That is fine. All right, let's go. I'm screenshotting smile. Hey, oh, 2 more cameras just came. Okay. One more time, one more time. Some cameras arrived last second. All right, keep smiling, keep smiling. Okay, cool. Thanks,
Great.
everyone.
Thanks, everyone. Very cool.
All right. If you don't want to have your camera on, you may flip it back off.
All right.
All right, Barbara.
Cool.
The floor is yours.
So, let's see. So I didn't see people put much in the chat. I hope you guys did get a chance to explore a little bit. If not, there's time. You can do it later. This is what I did. I explored this. What I did is I broadened my distribution a lot. And I made it I'm comparing labeled versus unlabeled data. And so this is the original distribution. What I did is I dramatically increased the amplitude of the distribution. So there was a lot of overlap in the way that these three clusters were made. So this is the original distribution and the original three random. I increased the amplitude each by a factor of 10 and added in the number of data points in each set and multiplied that by 6. And then you can see now the original guess, the original distribution and guess, but this is what the model ended up with. 3 clusters. And this is what generated those clusters. And so in this case, there really was the blue and the green overlapped too much. And so I just did an exploration of how much of this is really determined by the way that your data were formed and how much of it was just the way that the statistics fell. So I thought that was kind of, you can try lots of things. There are so many different parameters you can play with. And the nice thing about this one is it's very simple. All right. So, or at least it should be. Another form of machine learning, which is the kind of the easiest, one of the easiest ones to explain is a decision tree. We're not going to do these. you're going to hear. But basically, these are models where what they're doing is they're guessing, they're finding, they're applying criteria. They're deriving information from the sets of data, and then forming these routes that then applying more criteria. And then based on these routes, they're like, okay, if asking this series of questions, applying these series of criteria to the data, do they reproduce the decisions that we want the best? And so these are typically supervised methods. There are a couple of two common types of decision tree models are random forests and gradient boosting models. The big difference, I think, is that random forests are you're trying many different trees, and each of the trees get different votes, get to vote, and the aggregate of the performance of the trees is what the result is. Whereas a gradient boosting model learns from looks at the performance of a tree and how it's learning, and creates a consecutive tree, iterating to over time to look at the gradient of the improved performance and predict what the next tree should be. And so if you can imagine, these are different ways that you can do this. Great random forest gradient boosting models push towards convergence to get them there faster. And a cool example of decision trees in heliophysics is just looking for the propagation delay between an L1 observation where it's not exactly at L1, it's a spacecraft near L1, and Earth based on machine learning. So it takes different conditions, such as the location of the spacecraft relative to the exact Earth subsolar point, and find that if you use regular linear regression, it doesn't perform nearly as well as when you're using these trees to augment the way that you treat the data. The next example we're going to work on is our decision boundaries, classifiers, and support vector machines. And so these are typically labeled data. In other words, you're trying to in a decision boundary, you have data that are set. You have a n-dimensional space, and you want to create either a dividing line, or if it's more than 2 dimensions, a hyperplane, a plane that divides that data set into something that is, okay, this corresponds to this area, and this corresponds to the other area. A nice example of a support vector machine is a form of decision boundary where it's looking for, it's optimizing the divider through it and minimizing the error across the boundary of improperly assigned values on one side or the other. And these are nice because, again, you're not trying to do regression where you need a lot of rich information to populate that data site. You're just trying to say, okay, I would like to determine whether a flaring region on the sun will produce a coronal mass ejection or not. And I have tons of parameters. I have lots of magnetic field information. I have things like that. So what I want to do is take all those parameters and find a way to combine them all together to say, okay, is it on the yes CME side or on the no CME side via a hyperplane? And this paper also, in this description, this is in the Helio ML online book again, has an really nice example of interpretable machine learning. And so rather than just saying, this is what we got, they go into it and they're like, okay, why did we get this? Why did flares with these properties have CMEs, and why didn't they? What can we learn? And they did a nice job with that. Also, one of the best examples of data exploration is something that was written 6 years ago, but it's still so good. Ryan McGranagan's paper on predicting disturbances in the ionosphere that can distort or impede radio signals. This whole aspect of just, Ryan really is one of my mentors in this. When your model's trained, you're about a third of the way done, because you've now got a lot of work to do to take that model and turn it into knowledge. And Ryan does an excellent job of exploring all of that. All right, so our our second and third exercises focus on decision boundaries. However, you're going to need a little bit of information that's also because we're going to use activation functions. Oops, sorry. Let's see. I have to plug in my other computer because it's the one that I'm using for Q&A. There we go. Oh. All right. And so what I'm going to do though, in addition to the decision boundaries, I'm going to let's go into neural networks. Neural networks are usually what people think of machine learning, and I can tell you right away, I am not going to do better than 3 Blue, 1 Brown's video. It is excellent. And so what we're going to do is watch part of that video at the beginning, and I hope that you will like it so much you'll want to watch the entire series because it's so clear. So neural nets are the most, usually the most recognized of the machine learning models. They can be relatively simple or they can be extremely complex. They're basically matrices and functions. I mean, the simplest ones are really just, you're just multiplying a matrix and then applying a function to it to determine how you take the output of that matrix and send it to the next layer, which is just another matrix. And then in the end, you go back and you say, hey, how am I doing? And then you then you update based on how well you did another guess for the next time you go through. So the neural aspect of this is through an activation function. If you multiply matrix A times matrix B times matrix C, you get D. And the thing is that there's no reason for, there's nothing that's special about passing the A to B to C. You can just multiply those straight out and you get a matrix as an answer. And so the thing that makes it a neural net is the activation function. The activation function is something that doesn't just take the output of the matrix. It applies a weighting factor that can increase or decrease the strength of the value and thereby determine how much impact that element of the matrix has as it goes into the next layer. That's the neural aspect of it. And so you're not taking every piece of information and being like, this is all important. I want all of this. What you're doing is you're saying, okay, in this case, this is really important. This isn't at all. And those activation functions are very important because that's the neuron part. That's the firing part. When an activation function is high, it's equivalent to a neuron firing. Your brain has, when you're thinking, if all your neurons are firing at once, you can't think. You got to have you should only be when you're really thinking, you're firing the neurons that are relevant to the thought, and that's exactly why they call this a neural net. So these activation functions are the equivalent of firing of neurons. I like this article on how activation functions work. It's simple. There's a whole bunch of different types of activation functions. You can just say, hey, I'm going to give it a 1 if I like it and 0 if I don't like it. That's cool. It doesn't give you a lot of fine detail on whether you're close. There's, and also the one thing that's really bad about a binary activation function, in other words, your output is 1 or 0, is that it's not differentiable. There's a discontinuity, the derivative right here, which means that if you're at infinitely close to 0 from the right side and infinitely close to 0 from the left side, you have basically the same value, but the same value in X, and you have 2 different values in Y. And so the model cannot really improve because because this value it cannot improve in this area. So we like differentiable activation functions because then when the model is improving itself, it can see whether, okay, it has a slope. And then when we compute what we call back propagation, when we see how well it's performed, if we go back to the beginning of the model, we can see exactly how those values are fitting in and what their derivatives are. And so the rate of changes as they go back. We'll get to that in a little bit. But anyways, here's some, you're just going to see these common things. You're going to see there can be linear, sigmoid and tangent. I just showed sigmoid, but the hyperbolic tangent is like a sigmoid that's kind of squished a little bit. And then ReLUs are an example of where that's one where it's zero, it's really zero beyond a certain value. It's really one beyond a certain value. And so no information is really you're not changing stuff. But the gradient part is focused around this part where it could be 1 or 0. And so most of the training is focused in most of the modification of the model's behavior is focused in this area. A ReLU is one where it's kind of like if it's negative, it's just not, you've only got linear performance on the positive correlation end and not in the negative. That's so you have different models that will typically use these things. There's a lot of important parameters in building a neural net. There's the number of hidden layers. I don't like to call them hidden layers. I like to call them representation layers, meaning that every layer has a new way that it's reorganized your data. And so these are they call them hidden because they're not part of the input or output layer, but I like to just think of them as ways that you're looking the new ways of seeing your data. There are the number of neurons or perceptrons in each layer. And so a layer can consist of many neurons. And each layer does not have to have the same number of neurons. They just have to be, so you have your output of your one layer can feed into a layer with a different dimensionality. The activation functions are the things that then, once you have the output of a layer, determine what aspects of that layer have the strongest impact on the next layer. An optimizer is something that we won't really get into much, but an optimizer is the way that the model works to refine its next guess. And so if you do something where you're just guessing slowly, it can take a long time to converge. Or it can even find it can decide it's done a good job when it hasn't. There's a better solution, but it's kind of converged in one area that isn't quite the right one. So optimizers are different ones. And then finally, we do have our loss function and performance measure, the thing that tells the computer it's doing good, and the thing that the computer is trying to do its best at. And so we will build a neural network classifier model, but I just want to get into this a little bit more. A common performance measure is the loss function or cost function. It's called or performance measure. It depends on the model or who is talking. There's just basically what it is. It is an objective measure of how the model's doing. So a cost function is constructed from parameters that how far off the model is from perfect performance. Typically, it's trying to minimize. A good cost function is the purple one, where you have a nice minimum. And so the model can be working here, but it can be like, oh, but this one's better and this is better. And so the model's working to find a value that's the lowest value. And it's any change to this value is going to go up in either direction. And so you're like, oh, I'm good. If you have a bad cost function, you can have multiple minima. And cost functions, they're not necessarily 2 dimensions. They're whatever dimensions it's whatever dimension your model has. And so but you can have you can say, okay, you could have a double minimum. So like, let's say you think it's doing this and it's improving and it's trying to improve, but its guesses aren't very big. And it's like, oh, no, that's worse. That's worse. That's worse. That's worse. I'm done. But if it went here, then it'd be like, oh, wait, this is better. But it's, it just depends. And this one has a wide kind of flat, so this one could be, it could be very slow to converge because here the modifications the improvements are so minor. But either way, it's cost functions are what they end up being. It's good to get a good idea of how they're shaped in your parameter space. And they modify the model's output relative to the target output. It's rare to achieve perfect performance. So the objective of the model is to find a solution that minimizes this function, finds that part where it's like, okay, like the least squares fit. This line through these points contains corresponds to the distance of each point. The square of those points from the line summed is minimized. That's pretty nice. And that's what this is. And if I draw, if my slope of my line is here, or if my slope of my line is here, then the sum of the sum of the squares is larger. So it's not as good as this one. That's what the model's working to do. Yeah, so a common one is mean squared error. They're typically used in regression. You know, how far off was I from this? There are a variety of loss functions. I kind of like this one. Datacamp.com is also an excellent site for tutorials and things on things. And so you can decide a variety of loss functions and how they are commonly used. A lot of models kind of have loss functions built in, or at least default loss functions. You might want to figure it out. Optimizers are basically the model goes, it makes a guess. It just sometimes starts with random values, and it looks and it sees and it computes the cost function. And it says, I'm here, but then because you're the thing that created that cost is usually a sum of values that are outputs of the model. If your activation functions and everything are differentiable, it means that you can see what the slope is at this point. You can compute because you can see what the derivative would be. And so what you do is then you say, oh, well, I have the slope here is positive. And so my next guess needs to be negative, because I know that there's a lower value down here. And so if you have a really small learning rate, in other words, if you update each guess by a constant amount and it's really, really, really slow, it can take a long time to reach that minimum point. And this doesn't look bad because it looks like it had like 12 passes or something like that. But when you've got a huge, huge multidimensional data set with, 1 million data points in it, this can, it can take, there's a postdoc, he wrote a model that he was waiting for it to run, and he realized that it was going to take a year for it to converge as it was specified, because that's how slow it was, because it was just so much data, and the way then and the model itself for it to propagate through, evaluate the current performance, and then go back and compute the gradients and update the next guess based on all the slopes of the little elements inside of it. And it went and it was yeah, he said it was going to take I think he said 2 years. So we had to fix that. There's also one where if your guesses are so little teeny inches are too little. Also, if you guess too much, you're kind of jumping too much around parameter space. So a good optimizer is one that looks and says, okay, pretty sharp slope here. I'm going to guess this. And then it looks, and it doesn't just say, okay, not just the slope, what the slope is, but it also goes and it sees if the place where it landed up is consistent with what it thought it was going to end up. So it compares the rate of improvement over time. And for example, here, and this is a large vector, but it's a little shorter. And so I'm not going to jump so much. I'm going to jump a little smaller because the past two were when I saw, and so my next guess is going to be not so far off as it was over here. And then here, like, oh, this is now getting better. Look at that. It's getting close. So my next guess isn't going to be as much of a change either. And so a nice optimizer is one. It kind of applies friction to the point where when it reaches the minimum value, it doesn't even have much of an oscillation. This one, it could jump over, and it could, kind of float at the bottom. This is the problem here, is that this one's really having trouble making it to the bottom because it's moving too much. Anyways, so there's a simple gradient descent algorithm, which is basically just looks and then computes the gradient and then just goes and just keeps on moving towards the center. And then there's this adaptive moment estimation. I think that's One of the most famous optimizers, Adam, is one where it adapts. It looks for the moment, the momentum of the change, and it adapts then it chooses its next update based on what the momentum is. All right, this is a little hard to follow, which is why I'm going to run a video of how neural nets work. This is just a top-notch video, and I'm not going to run the whole thing, but just so you guys can see this, so it'll make a little more sense when we do the exercises.
This is a 3. It's sloppily written and rendered at an extremely low resolution.
Can you guys hear that?
Yes.
Okay, great.
28 by 28 pixels, but your brain has no trouble recognizing it as a 3. And I want you to take a moment to appreciate how crazy it is that brains can do this so effortlessly. I mean, this, and this are also recognizable as 3s, even though the specific values of each pixel is very different from one image to the next. The particular light-sensitive cells in your eye that are firing when you see this 3 are very different from the ones firing when you see this 3. But something in that crazy smart visual cortex of yours resolves these as representing the same idea, while at the same time recognizing other images as their own distinct ideas. But if I told you, hey, sit down and write for me a program that takes in a grid of 28 by 28 pixels like this, and outputs a single number between 0 and 10, telling you what it thinks the digit is, well, the task goes from comically trivial to dauntingly difficult. Unless you've been living under a rock, I think I hardly need to motivate the relevance and importance of machine learning and neural networks to the present and to the future. But what I want to do here is show you what a neural network actually is, assuming no background, and to help visualize what it's doing, not as a buzzword, but as a piece of math. My hope is just that you come away feeling like the structure itself is motivated, and to feel like you know what it means when you read or you hear about a neural network, quote unquote, learning. This video is just going to be devoted to the structure component of that, and the following one is going to tackle learning. What we're going to do is put together a neural network that can learn to recognize handwritten digits. This is a somewhat classic example for introducing the topic, and I'm happy to stick with the status quo here, because at the end of the 2 videos, I want to point you to a couple good resources where you can learn more, and where you can download. As the name suggests, neural networks are inspired by the brain. But let's break that down. What are the neurons, and in what sense are they linked together? Right now, when I say neuron, all I want you to think about is a thing that holds a number, specifically a number between 0 and 1. It's really not more than that. For example, the network starts with a bunch of neurons corresponding to each of the 28 times 28 pixels of the input image, which is 784 neurons in total. Each one of these holds a number that represents the grayscale value of the corresponding pixel, ranging from 0 for black pixels up to 1 for white pixels. This number inside the neuron is called its activation. And the image you might have in mind here is that each neuron is lit up when its activation is a high number. So all of these 784 neurons make up the first layer of our network.
Now, what they do here now is this is what we call a simply connected neural net. Rather than keeping it in that 28 by 28 pixel dimension, they're going to stretch it out and make it a chain. Now, if you can imagine, that might not be the most useful thing, because if you the rows have nearest neighbors that are close, but now the columns, their nearest neighbors, are no longer close to them. They're over in another place. And so that can, so that correlation, you can't really leverage that well. But for a simply connected neural net, every single one of these pixels is treated the same, no matter what the order they're in, because every single one moves to the has the same impact on the next layer. So more sophisticated neural nets have things like a convolutional neural net apply filters, which are spatially dimensioned, which compute a spatial component, and not only take a single value, but track that value relative to its neighbors. So this is the simple neural net. Convolutional neural nets, if you're trying to do images, that's the thing you want. But we got to start with something.
Now jumping over to the last layer, this has 10 neurons, each representing one of the digits. The activation in these neurons, again, some number that's between 0 and 1, represents how much the system thinks that a given image corresponds with a given digit. There's also a couple layers in between called the hidden layers, which for the time being should just be a giant question mark for how on earth this process of recognizing digits is going to be handled. In this network, I chose 2 hidden layers, each one with 16 neurons. And admittedly, that's kind of an arbitrary choice. To be honest, I chose 2 layers based on how I want to motivate the structure in just a moment. And 16, well, that was just a nice number to fit on the screen. In practice, there is a lot of room for experiment with a specific structure here. The way the network operates, activations in one layer determine the activations of the next layer. And of course, the heart of the network as an information processing mechanism comes down to exactly how those activations from one layer bring about activations in the next layer. It's meant to be loosely analogous to how in biological networks of neurons, some groups of neurons firing cause certain others to fire. Now, the network I'm showing here has already been trained to recognize digits. And let me show you what I mean by that. It means if you feed in an image, lighting up all 784 neurons of the input layer according to the brightness of each pixel in the image, that pattern of activations causes some very specific pattern in the next layer, which causes some pattern in the one after it, which finally gives some pattern in the output layer. And the brightest neuron of that output layer is the network's choice, so to speak, for what digit this image represents. And before jumping into the math for how one layer influences the next or how training works, let's just talk about why it's even reasonable to expect a layered structure like this to behave intelligently. What are we expecting here? What is the best hope for what those middle layers might be doing? Well, when you or I recognize digits, we piece together various components. A 9 has a loop up top and a line on the right. An 8 also has a loop up top, but it's paired with another loop down low. A 4 basically breaks down into 3 specific lines and things like that. Now, in a perfect world, we might hope that each neuron in the second to last layer corresponds with one of these subcomponents. That anytime you feed in an image with, say, a loop up top, like a 9 or an 8, there's some specific neuron whose activation is going to be close to 1. And I don't mean this specific loop of pixels. The hope would be that any generally loopy pattern towards the top sets off this neuron. That way, going from the third layer to the last one just requires learning which combination of subcomponents corresponds to which digits. Of course, that just kicks the problem down the road because how would you recognize these subcomponents or even learn? Hope is for one particular neuron in the second layer.
Quickly, but
in this layer
Yeah.
is going to be connected to all 784 pixel neurons from the first layer. And each one of those 784 connections has its own weight associated with it. Also, each one has some bias, some other number that you add on to the weighted sum before squishing it with the sigmoid. And that's a lot to think about.
So the sigmoid is the, in this case, is the activation function. That is the thing that I was showing in the previous thing where the sigmoid is 0 for far less than 0 and 1 for far greater than 0, and has a nice curve right around the transition from at the center from 0 to 1. And the bias is the thing. Well, let's say now that your transition is really it's not at 0. You're like, if it's greater than 10, it's good. If it's less than 10, I don't want it. If you subtract 10, then that moves your sigmoid close to 0. And so that's how that
is just
kind of
one
works.
along with 16 biases. And all of that is just the
And then finally,
So when we have a starting place for experimenting with how to change between one layer
Yeah.
and a particular neuron.
then finally, and this is something that's fun to work through. It's actually kind of fun. What you can do is then you can find out that when you have a guess and you look at and you go at the end, you evaluate which things are correct and which things aren't. All of this math, all of this stuff, all of these matrix multiplications and these sigmoid activations are differentiable, which means they have a slope, a positive or a negative. And so what you can do is you can what we call backpropagate. Once you've got the whole once you've got your output. There we go. Once you got your output here and you see that this is a, the input is a, let's find like, this is not in the, so this is a 1. Let's say that this was a 7 and it was telling you it was a 1. And so like what it does is then it takes all of the neurons that connected to this thing and goes back in what they call backpropagate, updates this weight, then updates these weights and updates these weights, and then gets back to here. And then all those weights now have been adjusted to something closer to something that would give you a 7. And so that's, again, it's not, there is a very good back propagation calculus section in here. I recommend it. For sanity's sake, I can't, but it's 3 blue, 1 brown. Excellent series of videos. And they are, and I do have the link in the tutorial materials. So anyways, now that we've gotten to that part, let's go to our next exercise. Our next exercise is boundary_simple in the same directory. So does anybody need help getting that pulled up? Julie, are we doing, Nat, we doing okay?
Looks
Or
like
I'm-
people are good.
Okay, great, great. All right, so this is gonna be easy. And I apologize, there are the GitHub, I thought I'd updated some of this stuff and I hadn't. And so some of this might not be exactly accurate. Anyways, in this case, the three elements of this model are we're going to take a data set, a false data set of flowers. The petal widths and the stem heights have been measured for all of these flowers. And the task is to classify them as either as iris or a rose. So these are labeled data, but there's only two options. And so what we're trying to do is we're trying to see if in this distribution of petal width and stem height, if there is a way that we can just draw a line and say, okay, if it's on one side, it's an iris, other side, it's a rose. And the performance or cost function is a simple mean squared error. So we have a couple of program parameters. So what we want to do is, first of all, epochs. Epochs are the thing that the number of times basically that you run through the whole data set. So in this, sometimes in the previous one in k-means, we did not define number of epochs. What we did is we said, when we get to the point where k is no longer updating, that's when it ends. In this case, we don't want this to run forever. So we might want to do, so what we do is we specify how many times it's going to send in a guess, look at the performance, compute the derivatives, go back, update all the weights based on those derivatives, back propagate, and then go back to its new guess and go back in. And how many out and backs there's going to be. Batch size is something that that limits if you update your guess each time, it's not very efficient. So what you want to do is you want to run through a set of parameters and then compute that, not just that cost function for that you'll do it for a set of parameters. So that's a very small batch size, but basically you do four guesses, and then you figure out how well they did, and then you update then you compute, and then you update your guesses based on those four, and you go back, and then you send the next four through. And so that's kind of nice, because if you wait for all 500 to run through and to update it, well, some of the finesse of where that gradient is, since you've got guesses all over the place, it might take a long time to converge. So batching is a nice way to make it converge quicker. Then you also have, you can have things, the learning rate. The learning rate is the thing that inches your guess along and modifies your guess. If you have too fast of a learning rate, it's not really learning, it's just shooting all over the place. And then you have your initial weights. These are the values that you're going to give, you're going to have for your first guess, because you don't know, in the beginning, the model doesn't know which are roses and which are irises. So in this case, and this is just a flag, we're going to do random, we're going to randomize our first guesses. So anyway, so for starting rates, let's see. So we've randomized our first guesses. We have a smallish learning rate, and well, actually it's a fast-ish learning rate, 0.02. And then now here's all of the program parameters. You have your activation, sigmoid. Then we need the derivative of the sigmoid, because when we go back and we figure out how we want to modify our guess, we need to continue that slope that we found we need to go back and surf along that surface all the way back. And so the sigmoid has so if you're near that sweet spot and there's a nice slope in that sigmoid, that's going to be the thing that helps you really effectively modify your next guess. And I apologize I know this isn't so clear. The only thing that works is to run it and to do it. This computes your loss. This computes the derivative of the loss, which is your first thing that you start to, the thing that tells you, your loss is the mean squared error. It's the y to the y hat squared. And so the derivative of your loss is the derivative of y squared is 2y. And so if you're differentiating within the loss, it's made negative 2y. Anyways, the forward pass is the thing that goes through, multiplies out your arrays, your input array to your weights. So it takes the output from one layer and multiplies it by the weights of the next layer, and then sends it into that sigmoid, that activation function, to become the end of the second layer. Backward pass, that's the thing that modifies it, goes back and modifies the weights for the next guess to refine the model. Yeah, and so anyway, so these are all, and then here, so this is the thing that computes based on the input, what the current prediction of the weights give you, whether it's a rose or an iris. And then finally, and then this is what we're going to do. We're not going to have a fancy separation boundary. We're just going to draw a line and see if we can draw a line that separates them. And so that's all we're doing, is making a line in space and seeing if something's on either side. So let's just run this, because it's painful otherwise. This is what the data set looks like. So this is my labeled data set. This is the stem height, and this is the petal width. And so if you've got short stem, long petals, you're more tending to be an iris. If you've got long stem and shorter petals, petals that are smaller relative to of the stem, that tends to be a rose. And so you've got this distribution here. And so what I want to do now is, these are the ones we have. Let's say I get a new flower. And I've measured the stem height and the petal width, and I want the model to tell me, based on those two values, if it thinks it's an iris, if it predicts it's going to be an iris or a rose. And so this is the main training loop. What it does is it goes through, it starts, initializes losses and things like that, runs through, I don't have much time, but I got to run through, goes through, makes a guess, computes the loss, sees how the loss is doing, and then it goes, oh, all right, I'm too far in this direction. So the derivative is so it computes the derivative of the loss at that point, and then that tells it how to move the loss backward pass into these weights through the different layers, and then it updates the weights. And it does this for all of the epochs, 500 epochs. All right, so let's go ahead and do this. And it finally, it computes the line and it draws the line. It's not perfect, but, but you could try different things and everything, but it says this is the prediction for this particular guess of this line, for this. But you can see now, and if we plot the loss curve as a function of time, which we've been storing, we can see that the loss was poor, and it very, very specifically went down, but it didn't get minimum loss, even after 500 epochs, 500 full sets of the data. It still isn't at the minimum value. It's not there yet. So this line is not the best line, because we're pretty sure that it can still improve. So, so let me do this. Now that's the reason I showed you that, is because I'm going to show you that's why we have packages. TensorFlow, Keras, scikit-learn. There's different packages and libraries that really make this so much easier. So we're not going to do that painful thing. We're going to do with TensorFlow exactly the same thing. And so what we're going to do is we're going to pull up two things. We're going to pull up sequential model. All that means is every layer feeds directly into the next layer. There's no fancy footwork or anything like that. And dense just means that every neuron is kind of treated equally. And so you're having, they call it dense connecting, meaning that like the 784 neurons in the first layer all go into every single point in the next layer. So we're going to choose 500 epochs. We're going to choose the batch size 4 again. We're going to load up the data. Now, if you don't have TensorFlow, just install it. And this is, so you see all of this stuff written out in here. Every single element of this model in here is all these functions are written out. Now, this is what you get when you have TensorFlow. It's here. That's it. You're saying it's a sequential model, meaning that you've got this is going to just be layer, layer, layer. You're going to add your input shape. Basically, it's just telling you that expect the input shape to be 2 values. And it's going to be 2 values. The model what we're doing is we're adding a layer, densely connected layer, only 1 layer, and the activation is going to be sigmoid. And then we're just going to go ahead and compile the and the loss is going to be mean squared error. And the optimizer, this is standard gradient descent. All it is, it just looks at the slope and updates it. Nothing fancy, no momentum, no nothing. And so you've got it all set up. Your model's done. 4 lines, really quick. This is what we're going to give you. This is the layers I want you to use. This is how I want you to treat the layers. This is how I want you to, this is your performance measure, and this is how I want you to meet that work towards improving that performance measure. Done. Then then you just say, fit the model. Oh crap. Okay, there we go. All right, I didn't hit the other one. You fit the model. That's all you do. And then you send it in, and then when you're done fitting the model, there we go. Now you can see our line. You can see our decision line, and it's the same thing, work better. It's a little better, not quite perfect. And but that's all it does. You can do that. If I wanted to do and so that is how easy it is. This is now plotline. What I'm doing here, what we're doing here is it's not assigning a label. All it's doing is seeing whether it's above or below the line, and that's how it's evaluating how it's doing. So anyways, so that's that. That's nice. Let's just move because I know I don't have much time left. This is the really fun one. I'm sorry I don't have much, but that video I showed you, here is a notebook that does that. Yay! We have we're doing sequential again. We have layers. We're going to implement something to make it a little faster called dropout. And we're just going to load this straight from a, it's already prepared for us. MNIST has this excellent data set, these characters. And what you do is, and it's already split out for us. Isn't this awesome? This is the X, we have 60,000 numbers, 28 by 28 numbers. And we also have, and they are all labeled. They're all labeled as the numbers that these 28 by 28 arrays represent. And it's already split out in a testing set. So they have a completely different random thing to assess how well it's doing on a separate set of variables. Believe it or not, people splitting out data sets they've done it poorly. They've accidentally reproduced some of their data in their training set, and then their testing set is not representative of performance because they didn't properly split it out. But in this case, they've done it for you. They're really nice about it. And then you can see that. So we have the 28 by 28 arrays, things. And what we're going to do now is we are taking it 28 by 28 and turning it into that 784 28 squared stretched input layer. Now, then like in the video, we have an array from 0 to 9 and representing the numbers 0 to 9. And so the labels are put into an input array. And so the labeled data. So if it's a 0, it becomes 1 0 0 0 0. If it's a 1, it's 0 1 0 0 0 0. And then if there's a very handy function in TensorFlow that just pops it right into that format, says there's 10 classes, just give me this thing where there's all zeros and there's this one that's hot here, and that's it. And could do that for these 2 sets, shove it in there. You can, yeah, and we can plot, let's plot it, see what it's looking like. Let's see. Now, these images were scaled images from 0 to 8. They're 8-bit images, and so they're scaled from 0 to 255. First thing that they do is they then rescale it from 0 to 1, like in the video. So rather than like an input ping, which would be 0 to 255, you go 0 to 1. Finally, now this is a little bit more, but you see very similar to before. It's a sequential model. Every layer feeds purely into the next layer. The input shape. The input shape is the shape of a single element that's going in. There's 768 value. It's an array of 768 values that represents a single character. You're adding a layer. It's a densely connected layer. In this case, our second layer, our first layer, our input layer is 768. This one's going to go to 16 by 16, so 256 units in it, using the sigmoid activation. We're going to implement something called the dropout rate. Yeah, thank you. Yeah, I'm almost at time. Actually, I'm over time, sorry. We're going to implement something called the dropout rate. The dropout rate is something, now, you can, instead of just always having all those neurons connected, you can arbitrarily ignore 25% of them. If you do that, it can converge faster, and it also is a great way to get rid of bad data. Like if there's bad data, if you can, there's times when it performs well if the bad data doesn't always hit your model. But anyways, so we're gonna move faster with dropout, and then we're gonna add a second layer. In this case, it's only an 8x8 layer, or 64. It's got 64 units with a sigmoid activation. We do another dropout. Our final layer is the output layer. This is the thing that is of the units of the 0 to 10, that because what we want to do is we want to compare the output layer to the labels that we created from 0, that 10 unit array. And the activation is something that's a little bit different. What we want to do is we want to turn it into a probability. Softmax goes through and it computes, it makes sure that the probabilities of all those from 0 to 9 adds up to 1. And so if you're really sure, then the 1 will light up with like 0.9 probability, and the sums of the other will be 0.1. If it's bad, then all of them will be about 0.1, or it'll be spread out across all of them. And so this is a different activation, still differentiable, but it lets you focus on a normalized probability across all of the values. And finally, we have the loss is just mean squared error, simple gradient descent, blump. And then let's train it. And this doesn't take too long. Notice we're going through 10 epochs. 10. Not 500. All right. Now we are going through, and what we're doing is let's just take a single weird, a poorly written character. That's sort of a 4. And so we're going to run the model on a single one of the test values, and one that we know is kind of crappy. And this is there. And so it gets it wrong. It guesses it wrong. And really, that's a terrible 4 anyways, and so it's there. But anyways, so the big issue with it is that the optimizer, we can do a better loss function, not the simple mean the RME. We can do something called cross entropy, where we're minimizing the entropy, or we're computing the entropy, and we're trying to minimize that. And the optimizer is Atom, which takes advantage of the fact that it's learned, not just updated it, but the learning rate. And watch this sucker. Watch how quick it goes. Bang. Well, actually, it's about the same. It's a little slower, but the nice thing is that now that we've run it through these epochs, let's see how this performs. And I'm sorry, I'm just a little bit late, just a little late. And I apologize for everyone. We didn't get a chance to really go in. I do have some exploration exercises at the bottom to kind of say, you know, what happens if you change the structure of the data sets? What happens if you approach this iris problem and this boundary wasn't a straight line? How would you approach the problem then? Also, we have hyperparameters for batch size, number of epochs. We have the optimizer, we have the learning rate. Which of these has, and also the number of data points in the first place. You know, how do which aspects of these values impact the speed, and which ones impact the accuracy, and which ones impact both? That's a thing that's really, because, you know, if something takes 10 seconds to run, and then it runs better and you get a more accurate model at 20 seconds, you don't really care. But if it takes 20 years, yes, you care. And so look at this now that we've got a good, we've got it, it's been, we have, let's do this again. There we go. This isn't 100% confident. That's a 9. That's pretty good. It's just taking a random value. Oh, that did pretty good. It's almost certain. It's 100% confidence 2. Let's keep on. There we go. Oh, that one's, look at that. I'm trying to find one that's not even, they're all like, it's performed so well. I can't find one that's got, there we go. There's a 5 that had 0.06% chance that it's not a 5. But basically, you know, you can go through and examine the different values. You can put noise in, see how it performs. And finally, I have several questions at the end. How they're doing. And how would you improve this? How would you make this work better? And how would you make it work in the real world? Almost all written stuff is dark on white paper, and it's not scaled properly, right? And so why do they give us this thing with a black background and white letters when that's almost never what we're going to use? And how do you generalize that to the real world? Finally, there are some excellent examples in this Helio ML online textbook of using much more sophisticated neural nets. There's one that's a convolutional neural net that takes advantage of spatial structure. And there's something called the long-term short-term memory neural network.
Hey, Barbara. Sorry, I had us muted. It always, stupid setting where I had it to automatically mute.
I have my volume up so high.
Oh, it's all good. Our Wi-Fi decided to die for like the last 2-ish minutes. So
okay.
We in the room didn't hear what you were saying, but
okay.
You can summarize in a sentence.
Oh, sure. Okay. Was it kind of up here, or like, where'd it die?
Before the what? Right before they introduce noise. Right before you introduce noise.
Okay. Oh yeah. So noise, you can see how that does because it's noisy. And then finally, I just have some exploration for you guys to try to ask, you know, what are these hyperparameters good with speed? Do they help with the speed or the accuracy? What are the hyperparameters? What are these things, these guiding principles of the model, and see how they work. Also, this data set, some of the numbers are poorly written, and you almost never get a white letter on black background. Almost all handwritten stuff is a piece of paper is white usually, or light color. It's usually a pen, you know. And so why are we working like this? And how would we, if you did need to go now and deploy this as something that detects, that translates numbers, these pictures into numbers, how would you do that in the real world? Because that's not the way that they're not going to be perfectly nicely framed things. Finally, there's some phenomenal examples in our field of, in this Helio ML textbook. They are, and two of the most common basic neural networks are ones that, again, don't do the simple connected perceptrons where every pixel is connected to every pixel in a layer. They take into account the fact that the nearest neighbors probably have more information, and also the nice thing about convolutional neural net is they have small filters which look at structure near the neighbor, and then they have large filters that look at the prevailing. And so convolutional neural nets are at the foundation of pretty much every facial recognition algorithm there is out there. When CNNs came out, they blew everything out of the water, because what they do is they convolve a filter to look for a gradient or an edge or an isolated, peak, a point or something. It finds those things and looks for the structure in this. And here's there's one where they use CNNs to enhance solar magnetic field images in this textbook. And finally, there is a great one on there's something called long short-term memory networks, where what it does is these are time series. It takes the trend of time, and what it's doing is it's trying to predicts and updates in time the predicted value and the real value, and it's trying to predict where it is going to be. And Matthew Argall did this because the MAG multiscale mission, it's very important for them to know when they're near a magnetopause crossings. And so what they did is they took some scientists identified magnetopause crossings and implemented this LSTM to be able to run as an algorithm that automatically is detecting when the magnetopause crossings are happening. So sorry, I'm a little over. I really want to thank everyone, and I don't see any questions, and I'm sorry I didn't leave any time for questions, but there's so much stuff. I can stick around the chat though during the discussion and answer questions.
Awesome. Thanks, Barbara. Do we have any questions for Barbara before break? We got one.
I think some of your exploration questions didn't quite get pushed to the repo, so you might want to just try to double check to make sure they're matching.
Yeah. No, I didn't. I stopped pushing because I was driving you crazy. And so I stopped pushing the text.
Thanks, Barbara.
Yeah. So so I will do a push. I will do a push right after this. So I apologize to everyone, but I'm one of those people, like I obsessively hit save. It's just one of those things. Like if you're editing a big document and then it crashes. And so I obsessively hit commit. And so my repository is insane. And so I was doing way too many little minor updates and edits. And so I stopped updating as soon as the code didn't change and the text, but there is text that hasn't changed. So I'll do it right now.
Hi, Barbara. One quick question about CNN. So do you suggest that computer vision is kind of like a subset of CNN, or do they use similar techniques?
Yeah, so there's a great book called Vision by David Marr that talks about how like vision actually happens. And there's like it's insane. Like the fact that you can just see barely a couple of shadows in a shape and you can know that's a human face. And so not all computer visions necessarily are CNNs, but they're kind of like that, because what they're doing, there's a very cool I can probably find this pretty quickly.
Barbara, can you
Ah.
maybe like zoom your screen
yeah.
a little? Yeah.
Yeah, yeah,
Thank
sorry,
you.
I'm just gonna really quickly find, I'm gonna show you how this, where is it? There's great examples of how, the thing is, I know there's one in Towards Data Science that's really good. So they show the actual activation shapes and they show how it performs. Darn it, there we go. That's a famous one. All right, there we go. So let me click on that. And it's Cora. Oh, why? Why do you hate me, people? I want to see this picture. There we go. There we go. Feature map. All right. So this is the first layer is often detecting weird little edges and boundaries. And so you'll see like this is a dark spot, this is a bright spot, here's like a thing, here's a bright and a dark. Here's there's different pieces. And so the first set of layers, the next set of layers, it starts to assemble. These are filters, these are gradients. And they're detecting sharp edges, slow changes, things like that. If you look at this middle layer, what it's done now is it started to take and what it does is it takes all of these detected things in your input image and it starts to assemble them into common features. So you can see, even though these are very simple reconstructions, there's an eye, there's a nose. And the weird thing though is that it's not about the boundary, it's about the gradient. There's no distinct boundary to the outer part of this eye. It's the gradient. There's no distinct boundary, in like an ear. It's all about the way the gradients are related. And then they assemble them. The final output or the final layer is where they've reassembled the picture into the reconstruction of all the filters. And then what it outputs is it outputs the, in that case, if it's a facial recognition algorithm, it will output who it thinks it is based on other, or whatever aspect it is. So yeah, so these are CNNs are kind of like when people say computer vision, it's usually something like it's usually got CNNs or some descendant in there. It's just but it doesn't have to. There are and then there are and a simply connected a pattern. There's all these there's UNets, ResNets. There's so many different types of neural nets where you don't have to just go one to one to one. You can actually interact between the layers a little bit too. Layers can have different behaviors and things like that, and they can also you don't have to go one to one. You can communicate across layers. And so if like you've got a little small feature and you're like, okay, but where does that land in the grand scheme of things? Oh, that's just that's a mole. We don't need this thing, or maybe that mole is very important for facial recognition or something, yeah, but I think that's pretty much, yeah, when they say computer vision, they're really talking about something that is taking the way that the human eye behaves, and the human eye behaves by detecting edges and gradients and assembles it into familiar structure and familiar things. And so, and CNNs right now are still, I think, the lead at being able to reproduce that. Don't have to be it though. Who knows? They might. I mean, there's definitely the only thing we know for sure is something better is going to come out. But,
Awesome. Thanks, Barbara.
Yeah.
There's another question, but we're going to throw it in the chat. We're going on break right now, but thank you very much again for coming on and talking about this with us.
Thanks. No, this was fun. I really appreciate it, you guys.
Yeah.
And if anybody has, we're going to try to generalize this into something that can be used for students in general. And so if anybody is experienced and wants to help improve this, let me know. We're going to make a separate repo with maybe a day-long course. Happy to have people do that. Happy to have people contribute.
Sounds good. Feel free to post about that in general on the PyHC Slack. All right. To everyone here in person, let's go outside and get a photo taken before we do our wrap up. But yeah, if anyone else is trying to figure out the public transportation back, apparently Nat, they have some good info on that. So when they are back in the room. Okay, it is officially 12:20. Let's see, I will stop screen sharing. Jack, are you online?
I am, yes.
Beautiful. All right, I know you had some slides to do. I'm just gonna go ahead and let you share and walk through that.
Okay. All right. Let me go ahead and hello, everyone. Okay, I'm going to talk quickly about finding solar data. Let's see, where is the share? Okay, here we go. All right, can you all see that?
No. Oh, well, the pin goes away if they start screen sharing.
Can
Yeah,
you
it's
see
just
that?
not sharing at the moment.
Okay.
Perhaps you have shared the wrong screen.
It's showing here that I'm sharing.
Maybe stop and start again.
How about
Aha!
that?
That is good.
Okay, thank you. Sorry about that. So this is a quick introduction into like finding solar data. And the project scientist for the Solar Data Analysis Center. So probably the first thing you want to do is just, let's see, have a look at the data, right? What you might be interested in. So this is a website called helioviewer.org, where if you know the kind of thing you're interested in, which spacecraft or instrument you're interested in, then you can go and find, go and browse that data before you even download everything. So you can think of this is like Google Maps for the sun. So that's the first site you can go to. Then if you want something to do something a little bit more sophisticated, then the next page is you can download a program called Helioviewer, which allows you to do more sophisticated manipulations of the data. So of the images of the data before you even download the data, right? So these two tools have access to a lot of different imaging data and are useful for finding out, for just looking at things before you start. Okay, next. So my main advice is to install SunPy and use the FIDO system inside SunPy. It's really great for downloading the data. So for finding and downloading the data. So once you've decided what you're looking for, install SunPy and use FIDO. Now you've probably come across FIDO earlier on in the week. It's a way of searching multiple data providers for data. Okay, so will I use it? FIDO is the same interface, it's the same code for lots of different data sets. So that means it's really easy. So if you're used to using FIDO for AIA data, you can use it for HMI data, for SOHO data, and so on. There's lots of data that's searchable. So all of the data that's through Virtual Solar Observatory, which is another data search system, features and events in the sun like active regions and sunspots. You can get through the Heliophysics event knowledge base and in situ data from CDAL Web. So there's lots of data you can get through FIDO. It's also very powerful. So you can do like logical and or queries. So like say like I want data from RESI and AIA. You can do that kind of query just in one line. And you can also search on like feature and event properties. So say you want a flare of a certain size and only flares above a certain size, and you can do that using FIDO. Now, one of the great things about it is there's extensive documentation and examples, and because that documentation is so extensive and the examples are so great, the SumPy team has spent an awful lot of time working on that. I'm not going to actually show you any of that. I would encourage you just to go there and read it, right? But here's a quick diagram of how FIDO kind of operates. So the user sends some queries to the FIDO through the FIDO code, and then FIDO talks to a whole bunch of different data providers. The Virtual Solar Observatory, as I said, the Heliophysics Event Knowledge Base, the Helio system, which is based in Europe. And it also has, FIDO itself is quite extensible. So you have data sources which are not covered by other data providers are covered in FIDO. And so the queries go out to FIDO and then the results come back. So really, as a user, you just interact with the FIDO software and you get access to a multitude of different data sets. As I said, the documentation is great. And for examples of how to get data, how to query data, and how to download it, go to docs.sumpy.org. And they have tutorials, how-to guides, example galleries, and so on that really go into detail and will lead you through. So for example, this is the SumPy tutorial on acquiring data. So this page will tell you all will lead you through how to get data using the FIDO interface. Every time SumPy is updated, these documents are also updated, and all three, if you're using an older version of SumPy, all that documentation will be available too. These are examples of like specific code examples of getting data through SumPy. So as mentioned, CDAW is accessible through the FIDO interface. So using FIDO, you can get to remote sensing data like images of the sun, and you can get in situ data, like what happened in interplanetary space when something went off in the sun. So all the data, all the examples and the code that you will need are on docs.sumpy.org. And as I said, the best way to get data into a Python environment is to use FIDO. That's all I have. Any questions?
Any questions in the room for Jack? Or online? All righty then.
Actually, can I have one real quick? This is Sean here.
Yeah, go ahead.
I had never seen that Helio viewer tool that you used before. You showed that you could like rotate around 3D plots and stuff. Could you maybe just spend a second more saying what extra stuff that has? I'm curious.
Well, it has a lot of extra stuff. So it's a Java and C++ application that is mainly developed at the Royal Observatory of Belgium and uses the same data sources that helioviewer.org uses. So it has, it has more sophisticated like reprojection capabilities than helioviewer.org has. And you can stream movies to your in the application, you can stream movies like of any particular time range using that application. You can also do solar feature tracking. So that's something that a lot of people like to do, where you sit over a spot on the sun and track just sit on top of that spot rather than having the sun sort of rotating around. You sort of, it's as if you're like sitting on top and looking at that particular feature in the sun. So jhelioviewer.org, download it. It's under development. Well, I should say it's under constant refinement, so it's always up to date. Try it out. It's great.
Yeah, that's great. And the URL was jhelioviewer.org.
Yep. Yep.
Thank you so much.
Any other questions? All right. Thanks, Jack. Okie dokie. We're on to the last presentation. Me. All right. Oh, God.
I have slides as well, Julie, for the non-solar data.
Oh, my God. I'm sorry. You're on here too, Eric. I will stop and let you go. Stop share.
Cool. Hopefully the share screen works. Let's see. Screen 2, share. Can you see it?
Yeah.
Is it sharing? Doesn't look like it.
Jack had to stop and restart. Maybe that will help.
Maybe if I reconnect, I'll try reconnecting.
We see your screen, Eric.
Okay, cool. Let's see. All right, so my name's Eric Grimes. For those of you who don't know me, I work at the SPDF team at Goddard Space Flight Center. I've been here for 275 days now, so 9 months. And I'm going to be talking a little bit, very little bit, briefly about searching for non-solar data in heliophysics. So if you go to the SPDF website, which is linked on the first page here, it's just, of course, spdf.goddard.nasa.gov, or you could just Google SPDF NASA, and it'll take you to the website, to our website. On our new website, you just to find the Heliophysics data portal, you just go to the Data Access and Orbit Services dropdown, and it's the very last link. So I just suggest just going to that link, and it'll take you to this page, the Heliophysics data portal, which searches the SPACE metadata for a large number of data sets. So in addition to the text restriction input box, you'll probably end up wanting to use the element restriction section to limit the output. And this page contains the dataset names. So a list of it contains a table with the dataset names with the link to the SPACE description, as well as another column that has information and access links for each dataset. And again, this is just coming from the SPACE registry. So for example, you can just set the observatory and the element restriction to discover if you want to search for discover data. Set the measurement type to magnetic field, and you'll find all of the B field data sets for the Discover mission. And that includes links to the SPACE descriptions, as well as the various ways of accessing the data. So direct access to the CDF files, as well as access to the C2Web Happy server, as well as and C2Web. So all the data sets that are on C2Web in the system should have a link to C2Web.
One thing to note is that I suggest using quotes in the text restriction box if you, for exact matches, if you have multiple words. Otherwise, it does this strange thing where it searches for all of the space items that have one word or essentially one. Like if you search for magnetic field, it'll search for all of them that have magnetic or field in the description. So use quotes around magnetic field to actually find all of the ones that are limited to magnetic field. So this is what happens when you click on the link of the product name. It sends you to the space description, and it's cut off at the bottom, but it has the full space description for the data product on that page, and it's rendered in HTML, and it has data access links up in the upper left, so you can access it from the find the Happy server, as well as a link to CDWeb and direct links to the CDF files. And since this is a Python meeting, there's also a library for searching the Heliophysics data portal web services. And I included a link here. It's just the same heliophysicsdata.goddard.nasa.gov/web services. And there are Jupyter notebooks that show how to access and search this programmatically using Python. I think most people on here probably don't actually want to implement their own search engines though. So I suggest using the website before implementing your own search engine and doing it in Python. So one thing that I really wanted to show as well is what happens when you are. So one of the things that I wasn't aware of before starting at SPDF is that there's a feature buried in the CDWeb interface. So if you click on the CDWeb, the link for CDWeb, for a data set, and then you go to the CDWeb interface and say, for example, put in discover and magnetic fields, and you get a link or you get a list of the data sets that we have in the CDWeb system. Usually people just want to select the data sets and create browse plots, but there's also this link here to info and metadata. And if you click on info, and I didn't know this for the longest time, but if you click on info, it'll give you the information about that data set and a list of variables, but also there's a link down here that says data access code examples. And you click that link, it will take you to a page that has a launch binder button that will actually launch a Jupyter notebook showing you how to access that data set and binder. And if you don't want to wait on binder to load the Jupyter notebook, you can also, there's a script that you can just copy and paste into your terminal for accessing that data set. And this exists for most of the data sets in CDWeb. It also includes installation instructions up at the top commented out. And so, for example, this is what the Jupyter notebook for that Discover Mag data looks like. It includes showing how to load the data into X-array objects, as well as the data and the metadata for a time range. And that's all I had. Thank you.
Thanks, Eric. Anyone have any quick questions for Eric? All right.
So if you do have questions later, go to our website. At the very bottom, there's a link to our email, our support email. You can just email SPDF. We're very responsive to emails.
Good to know. Thank you.
Thanks for listening.
If you could email your slides to me too, that'd be great. All right.
Will do.
Thanks. Cool. Now we're at the final presentation. Going to go ahead and fix this. Okie dokie. All right. Well, just a quick wrap up. I don't want to belabor anything too long. I know people are hungry, and then we've got a mountain to go walk up for some of us. So I just want to start with a bunch of thank yous to people. So Huge thanks, obviously, to LASP, where Sean and I work here, for hosting us and making this meeting possible. To NASA for funding mine and Sean's activities to make this happen, as well as some travel for some of our presenters. NSF for funding several of our summer school attendees that came here via that travel aid. So that was awesome. Thank you. Leah Park, who works here at LASP, she helped out a lot with getting badges and parking and room scheduling situations figured out. Obviously, facilities for setting up the room, our front desk for the signage and helping y'all in general, IT for setting up and handling AV. And then our presenters for their hard work in putting together all the different tutorials and PyHC challenge ladder exercises and so forth. You guys made this summer school what it is. The org committee for all because I'm on it, hard work in putting all this together. Those who contributed to the PyHC challenge ladder prizes. And then, of course, all of you here in person and online. For making the trip out here if you came, or for hopping on Zoom for so long and taking time out of your schedules to come to our summer school, for asking such great questions and contributing to the materials, and generally just for participating. So big thank you to y'all. All right, I'm gonna put like a screenshot of this slide probably directly in general, but if you want to save everything from Helio Cloud, this is how you'll do it. And do it, I think next Wednesday is June 3rd, or maybe that's Friday. I forget. By June 3rd, the date is the one that's correct. Make sure to get all your content saved. We also will forever have all of the notebooks and things of that sort posted in our GitHub. So if you just go to heliophysics.py/summer-school-24 on GitHub, you will find all the materials here. And if Peter can come up and explain this a little, he also recently put together a package that helps have Helio Cloud at home.
Thank you. So there are a couple questions about like running the notebooks outside of Helio Cloud, because we will be taking down the instance after a week. I think the date was June 3rd when the instance will be down. So if you want to run the notebooks on your own machines, you need to download following those instructions. And then I also set up this little Docker environment that you can set up on your machine. This loads up the image that was ran on all of your servers on Helio Cloud. So it comes with all of the PyHC dependencies, because right now we don't really have a PyHC core library that you can just install via pip. So this would be a way for you to run all of those notebooks and test out those libraries on your home machines. And yeah, so the link's there. I also posted it in Slack if you want to check it out. I provided some build and installation instructions on there as well. If you have any issues doing so, feel free to open up an issue or send an email on the Helio Cloud website. You can email us there, or even through PyHC, or even message on Slack, or even suggest a change via pull request. But yeah. Oh, this link has since changed, the one that's actually on the slide. This one has my personal repo. I transferred it to PyHC ownership. So yeah, they'll check out the link in the chat. Yeah.
Good news for that, Peter. I actually tested it, and GitHub automatically redirects you from that link to the updated one.
I think there's like a certain time on that. Maybe it's like a day or a year. I don't know. But GitHub will eventually flush that out.
Yep.
All right, cool.
Yeah, I'll update the link in these slides. So if you go to look at these later, it'll be up to date. Thank you. And thanks for putting that together last minute. That's awesome. Just a couple other notes. We'd really appreciate getting feedback from y'all on the summer school and how it's gone, what you liked, what you think could be improved for the next time, so we can make it an even better experience on our third try. So that would just involve going to this URL here, tinyurl.com/PyHC-school-feedback. And if you can fill that out before next Friday, that would be awesome. Even better if it's sooner. If you're one of the in-person presenters for a poster, please submit that to our Zenodo collection for long-term archival. Also, a bonus, it gives you a DOI so that you can cite your efforts and the work you put into that here. Finally, actually second to last point, we're not going to be immediately like closing down the PyHC summer school Slack space or anything, but it will be cleared out at some point so that the next rendition of the summer school, when we pull this up again, doesn't have to look at a bunch of old content. So yeah, just know that. And if you want to stay in contact with PyHC, ping me, send me an email, or go to our contact page for more information on how to get onto our permanent PyHC Slack space. And if you want to rewatch any of the summer school content, it's all on YouTube. Here's the link. Go see it. These slides will be saved definitely in a Google Drive folder, as well as on the GitHub here. So I'll point you to the link for that so that you can get these links later on too. Oh, yeah, connecting after the summer school. I'm asking all the PyHC devs to kind of be on this summer school Slack space just for the following week after this. You can just check it once a day or something. If people have questions, feel free to put it in the various package channels they're in. After that, you're going to need to contact the devs via email or their own various discussion channels. Some have Slack spaces, some have Discords and so forth. And we'll email out those points of contact after. And if you want to connect with PyHC after the summer school, again, join our Slack, go to our webpage, Helio Python. If you go to pyhc.org, it just redirects to that. But it's all under contact, so you can figure out how to stay connected. And yeah, thank you again, and hope to see you all in the future. You're free to stop staring at the screen and go about your lives. If you're going to be hiking, maybe gather up here and we can figure out our lunch plan.